We all live our lives with a fundamental assumption, a quiet belief so deeply ingrained we never think to question it. That the world around us exists and unfolds in a predictable way, even when we're not looking. That the moon is still in the sky when you close your eyes. That a tree falling in a forest makes a sound, whether or not anyone is there to hear it. This is the bedrock of our experience, the silent agreement between our minds and the universe. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. But what if this comfortable story we tell ourselves about an objective, independent reality is incomplete? What if the most successful, most rigorously tested theory in the entire history of science suggests that the world might not be so solid after all? What if reality itself is shy? What if it waits for us, for an interaction, to decide what to be? This isn't a philosophical riddle. This is the central, quiet mystery at the heart of quantum mechanics. It is a story of how a simple experiment with light revealed a profound question about everything we thought was real. A question that suggests our relationship with the universe is far more involved than we ever imagined. Today, we are going to pull on that thread and see how much of our perceived world unravels. We'll explore the experiments that reshaped physics and the rival theories that tell different stories about the soul of reality itself. By the end, the simple act of looking at the world may never feel the same again. The quantum weirdness begins, the double-slit experiment. To understand how our stable, classical world begins to dissolve, we have to start with an experiment so simple, yet so profound, it has fascinated physicists for over a century. It's called the double-slit experiment, and it is the perfect illustration of where our intuition gives way to the quiet strangeness of the quantum world. Imagine a wall with two thin, parallel slits cut into it. On one side, a machine fires tiny objects, let's say marbles, one by one. On the other side, a detector screen records where each marble lands. The result is simple and intuitive. The marbles that go through the left slit hit the screen behind it, and those that go through the right slit hit the screen behind that. You end up with two distinct bands, a direct map of the two slits. This is common sense. It is the world as we know it. Now, let's switch from marbles to something much smaller, electrons. Electrons are fundamental particles, tiny components of the world around us. We can fire them one at a time, just like the marbles. You would expect the same result, two bands on the screen. But that is not what happens. Instead, as thousands of individual electrons build up, what appears on the screen is an interference pattern. This pattern is a series of many light and dark stripes, like the ripples you see when you drop two stones into a pond. This interference pattern is the unmistakable signature of a wave. This result is deeply strange. It suggests that each individual electron, fired one at a time, is not behaving like a particle. It is behaving like a wave, seeming to pass through both slits at the same time, interfering with itself, and then arriving at the screen. A single electron appears to be in two places at once. This is where the story takes its first quiet but dramatic turn. The physicists who first saw this were, understandably, perplexed. They decided to try and see which slit each electron was actually going through. They set up a detector, a sort of tiny sensor, right at the slits, designed to record which path each electron takes. And then, the universe showed a different face. The moment the detector was turned on, the moment the experiment observed which path the electrons were taking, the interference pattern vanished. In its place were two simple bands, exactly like the ones the marbles made. The electrons, as if their wave-like nature was a private affair, immediately began behaving like predictable little particles. Simply by being measured, their ability to be in two places at once disappeared. The very act of measurement forced the electron to have a single, definite path. The outcome of the experiment depended entirely on whether or not it was being watched. When no one was looking, reality was a haze of possibilities, a wave of potential. But the moment an observer tried to pin it down, reality settled into a single, definite state. This isn't just a curious side effect, it's a fundamental aspect of the quantum world. And it leads to a quiet, humbling question. If a particle's reality is a spread-out wave of possibilities until it's measured, what about the rest of the world? Does the moon only truly occupy a definite place when you, or something, is looking at it? This single experiment challenges the illusion of a passive, objective reality. It suggests that the observer is not a separate spectator, but an active participant in what becomes real. The Copenhagen Interpretation, reality on demand. The shocking results of the double-slit experiment required an explanation. In the 1920s, a group of physicists, led by the brilliant minds of Niels Bohr and Werner Heisenberg, developed a framework to make sense of this new, unfamiliar reality. Their solution became known as the Copenhagen Interpretation, and for a long time, it has been the most widely taught explanation of quantum mechanics. At its core, the Copenhagen Interpretation makes a bold claim. There may be no deep, concrete reality that exists independently of measurement. At the quantum level, the world exists as a cloud of possibilities, described by a mathematical tool known as the wave function. This wave function describes all the possible states a system could be in, all at the same time. This state of existing in multiple possibilities at once is called superposition. So, before it's measured, the electron isn't going through the left slit or the right slit. According to this interpretation, it is in a superposition of going through both. So where does the definite reality we experience come from? This is the second crucial piece of the Copenhagen puzzle: the collapse of the wave function. Bohr and his colleagues proposed that the act of measurement, an irreversible interaction with a measuring device, does something dramatic. It forces the system to abandon its state of superposition and collapse into one single, definite state. The moment the detector at the slits is turned on, the electron's wave function collapses. The cloud of probability condenses into a single point. The electron is no longer in a superposition. It is now definitively at either the left slit or the right slit. The observation didn't just reveal where the electron was. It seemed to finalize the reality of its position. Before the measurement, the question, which slit did the electron go through, was, in a sense, meaningless. The act of asking the question, through an experiment, forced an answer into existence. This idea was nothing short of revolutionary and led to a famous series of debates between Niels Bohr and Albert Einstein. Einstein, a firm believer in an objective, predictable reality, found the implications of this interpretation deeply unsettling. He famously argued, God does not play dice, believing there must be some hidden variables, or deeper properties we just hadn't discovered yet. For Einstein, reality was rock solid. The moon is there whether you look at it or not. Bohr, on the other hand, argued that the quantum world simply does not operate by the same rules as our everyday world. He introduced a concept called complementarity. This principle states that quantum objects have pairs of properties, like their wave-like and particle-like nature, that you can't see simultaneously. By setting up an experiment to measure which slit the electron goes through, its particle nature, you inherently lose the information needed to see its interference pattern, its wave nature. You can see the particle, or you can see the wave, but you can never see both at once. They are mutually exclusive realities, and the experiment you choose to perform determines which one manifests. The Copenhagen interpretation, therefore, drew a line between the fuzzy, probabilistic quantum realm and the definite, classical world of our measuring devices. But this raised a difficult question. What exactly counts as a measurement? Does it have to be a complex apparatus? A camera? A single photon bouncing off the system? The interpretation was vague on this point, creating what some called a shifty split between the two worlds. It was this very ambiguity that led another brilliant physicist to devise a thought experiment so vivid it would become the most famous paradox in all of science. Schrödinger's cat, the paradox in the box. Enter Erwin Schrödinger, an Austrian physicist who, like Einstein, was deeply troubled by the philosophical implications of the Copenhagen Interpretation. In 1935, he devised a thought experiment to highlight what he saw as the absurd conclusion of applying these quantum rules to the macroscopic world we live in. He wanted to take the strangeness out of the subatomic realm and place it squarely in our everyday reality, using a now famous, and thankfully hypothetical, cat. Here is the setup. Imagine a steel box, completely sealed off from the outside world. Inside, we place a cat, along with a device containing a single radioactive atom, a Geiger counter, a hammer, and a vial of poison. The laws of quantum mechanics govern the atom's decay, making it a truly random event. In 1 hour, there is a 50% chance the atom will decay and a 50% chance it will not. The Geiger counter is set up to detect this decay. If it does, it will trigger the hammer. The hammer will then shatter the vial of poison, and the cat will die. If the atom does not decay, nothing happens, and the cat remains alive. Now, we seal the box and wait for 1 hour. At the end of the hour, we ask a simple question. Is the cat inside the box alive or dead? Our classical intuition tells us the answer is obvious. The cat is either alive or it is dead. We just don't know which one until we open the box. The act of opening the box is simply an act of discovery. But this is where Schrödinger applies the Copenhagen interpretation and reveals the paradox. According to the theory, the radioactive atom, being a quantum system, is not in a definite state until it is observed. Until a measurement is made, the atom exists in a superposition of both states, decayed and not decayed. But the fate of the cat is directly linked to the state of the atom. If the atom is in a superposition, then the Geiger counter must also be in a superposition of triggered and not triggered. The hammer must be in a superposition of fallen and not fallen. And therefore, the cat itself must be in a superposition of being both alive and dead. According to a strict application of the rules, until the box is opened and an observation is made, the cat is not one or the other. It is, in a very real, mathematical sense, a blend of both possibilities. The entire system, atom, hammer, cat, is described by a single, complex wave function. Only when an observer opens the lid and looks inside does the wave function for the entire system collapse. In that instant, reality is forced to choose. The atom snaps into a definite state, and the cat is found to be definitively dead or definitively alive. Schrödinger intended this to show the strange consequences of the interpretation. He was essentially saying, your theory leads to this. But cats are not both alive and dead. We know this. Therefore, the theory must be incomplete. He highlighted the problem of where the measurement happens. Is the Geiger counter the observer that collapses the atom state? Or does the counter also enter superposition? What about the cat? Is the cat itself an observer? Or is it only the final measuring apparatus, or conscious human, that completes the act? The paradox doesn't prove that quantum mechanics is wrong. Its predictions are unbelievably accurate. What it does is lay bare the profound philosophical chasm between the quantum world of probabilities and the classical world of definite outcomes. It forces us to confront the role of observation head-on. If the cat is both alive and dead until we look, it feels as though our simple act of looking reaches into the box and solidifies reality. Schrödinger's cat was not meant to be a statement about reality, it was a criticism. But in its quiet persistence, it became the ultimate symbol of the central mystery. Does the world wait for us to look before it becomes real? Pushing the boundaries, the quantum eraser. If the double-slit experiment and Schrödinger's cat weren't enough to stretch your sense of a stable, objective reality, there is an experiment so subtle and counterintuitive that it challenges our very understanding of cause and effect. It is called the delayed choice quantum eraser, and it takes the observer effect to its most extreme conclusion. It suggests that not only does observation affect the present, but that the story of the past can be recontextualized by information in the present. Let's build on the double-slit experiment. We know that if we have which slit information, we get a particle pattern, two bands. If we don't, we get a wave pattern, interference. Having that information seems to destroy the wave behavior. The quantum eraser is designed to see if we can get that wave behavior back by erasing the which slit information after the particle has already hit the screen. Here is a simplified version of how it works. We start with a special crystal that splits a single photon into a pair of entangled photons. Entanglement is another quiet quantum mystery where two particles become linked, their fates intertwined no matter how far apart they are. One photon, the signal photon, travels to a main detector screen, where it helps build up a pattern. Its entangled twin, the idler photon, travels on a separate, longer path. The way the photons are created means the idler photon carries the which slit information for its signal twin. Because this information exists, the signal photons arriving at their screen create two simple clumps, a particle pattern. So far, this is consistent with what we know. But here is the twist. The experimenter can make a choice for the idler photon. They can either direct it to detectors that preserve the which slit information, or they can send it through a scrambler that effectively erases that information, making it impossible to know which path its twin took. The delayed choice part comes from making the idler's path much longer. The signal photon hits its screen and its journey is over, before its idler twin even reaches the choice-making setup. Here's what happens. When the experimenters look at all the data from the signal photons, it just looks like a random blob. But then, they use the information from the idler detectors to sort the signal photons. They look only at the signal photons whose entangled twins had their which slit information erased. And when they do that, an interference pattern emerges from the data. A wave pattern. Then, they look at the signal photons whose twins had their information measured. That group forms a particle pattern. Think about what this means. The pattern formed by the signal photons depends on a choice made about their twins, a choice that happens after they have already landed. This does not mean the future is changing the past. No signal can be sent back in time. Instead, it suggests something more subtle and profound. The reality of an event is deeply connected to the information available about it, even if that information is collected later. The story of what happened wasn't finished until all the information was gathered. It reinforces that reality is not a fixed, linear narrative. The properties of a system are defined by the total information available, and the fact that this information can be finalized after the event has seemingly concluded only deepens the strangeness. An escape hatch? The many worlds interpretation. The Copenhagen Interpretation, with its collapsing wave functions and special role for measurement, left many physicists feeling uneasy. In the mid-1950s, a graduate student at Princeton named Hugh Everett III proposed a radical, elegant, and mind-stretching alternative. An idea that did away with the observer, did away with the collapse, and did away with the idea of a single reality. This was the birth of the many worlds interpretation. Everett asked a simple question. What if the wave function never collapses? What if the Schrödinger equation, the fundamental rule of quantum mechanics, is the only thing that governs reality? In the Copenhagen view, there are two processes: the smooth evolution of the wave function, and the sudden collapse during measurement. Everett said, let's just keep the first one. So what happens when Schrödinger's cat is in the box? In the Copenhagen view, the universe randomly picks one outcome. In Everett's view, the universe doesn't pick. It does both. According to the many worlds interpretation, MWI, at the moment of the quantum event, the entire universe splits. The wave function doesn't collapse, it branches. In one branch of the universe, the atom decays, and the cat dies. In another, parallel branch, the atom does not decay, and the cat lives. You, the observer, are also a quantum system. When you open the box, you split too. There is a version of you in one universe who sees a dead cat. And there is another version of you, in a completely separate, non-communicating universe, who finds a living cat. Both outcomes happen. Both are equally real. This elegantly solves many of the problems of the Copenhagen interpretation. There is no more shifty split, because everything, including observers and measuring devices, is quantum. The wave function collapse, an extra rule, is gone. Reality is just the universal wave function, branching and evolving through time. In the double-slit experiment, the universe splits. In one universe, the electron goes left. In another, it goes right. The interference pattern arises from the interaction of these parallel realities. The many worlds interpretation is, in a way, far more conservative in its physics. It doesn't add a new rule like collapse. It just takes the existing math and follows it to its logical conclusion. But its conclusion is anything but modest. It implies the existence of a staggering, perhaps infinite, number of parallel universes. Every time a quantum event with multiple outcomes occurs, the universe branches. There's a universe where you turned left this morning, and another where you turned right. The price of getting rid of the observer who creates reality is an infinitely branching multiverse where every possibility is made real. For its critics, this seems to violate the principle that the simplest explanation is usually the best. Is postulating countless unobservable universes really simpler than accepting the collapse? And while the theory has trouble explaining why we perceive probabilities if everything happens, other developments like decoherence have offered potential answers to these challenges. So, we are left with a stark choice. One story gives us a universe where reality is a haze of potential, waiting for measurement to bring it into focus. The other gives us a vast, ever-growing multiverse of concrete realities, where we are just one version of ourselves, on one path of an infinite cosmic tree. The supporting cast, decoherence and other ideas. The debate between Copenhagen and many worlds isn't the only story. Physicists have searched for other explanations that might bridge the gap between the quantum and classical worlds. One of the most important ideas is a process called quantum decoherence. Decoherence helps to explain why we don't see quantum strangeness in our everyday world. The core idea is that no quantum system is ever truly isolated. It's constantly interacting with its surrounding environment in tiny, subtle ways. A stray photon, an air molecule, a thermal vibration. According to this theory, these constant, unavoidable interactions are what destroy quantum superposition for large objects. The quantumness of a system is incredibly fragile. When a system in superposition interacts with its environment, information about its state leaks out and becomes entangled with trillions of other particles. Think of a drop of ink in a lake. At first it is concentrated, but it quickly interacts with the water, spreading out until its information is dispersed and the distinct drop is gone. This process happens astonishingly fast for an object like a cat. It would be bombarded by countless air molecules and photons, each interaction acting like a tiny measurement. The environment itself effectively observes the cat, causing its superposition of alive and dead to decohere almost instantly. In this view, observation doesn't require a conscious mind. It just requires an interaction with an environment that carries away information. Decoherence is a crucial piece of the puzzle and has been experimentally verified. It explains the asterisk appearance of wave function collapse. However, it may not fully solve the problem on its own. The math of decoherence still describes the entire system, object plus environment, as being in one gigantic superposition. It just pushes the strangeness further out. For supporters of many worlds, decoherence is the mechanism that separates the branching universes. For others, it helps define what a measurement is. Other ideas exist, too. Bohmian mechanics, or pilot wave theory, suggests that particles do have definite positions at all times. They are guided by a real, physical, pilot wave. In the double-slit experiment, the particle goes through one slit, but its wave goes through both, guiding it to create the interference pattern. Observation doesn't create reality, it simply reveals a pre-existing state. Each of these ideas is an attempt to build a coherent story about the world that is consistent with the quiet, strange, but undeniably successful predictions of quantum math. The implications: why does this matter? You might be thinking that this is all abstract and philosophical, a debate with little bearing on our actual lives. But the implications of this question are both quiet and profound. On a practical level, the rules of quantum mechanics are the foundation of our modern world. The computer or phone you're using works because of transistors, which are designed using quantum principles. Lasers, GPS, MRI machines. All of this technology exists because the mathematical predictions of the theory are fantastically accurate. The philosophical implications are where things become truly humbling. If we consider the Copenhagen view, it suggests that the observer has a unique role in the cosmos. It elevates observation from a passive act to a participatory one. The physicist John Archibald Wheeler once said, "No phenomenon is a real phenomenon until it is an observed phenomenon." In this view, the universe, in some sense, had to give rise to observers to bring its own reality into being. Then there are the implications of the many worlds interpretation. If it is correct, then every quantum event has spawned new universes. This means there are countless versions of you living out every possible life. This reframes our notion of identity. Your choices are real and have consequences in your branch, but from a God's eye view of the multiverse, all roads are taken. The debate also challenges our concept of time. Experiments like the quantum eraser suggest that our linear, forward-moving perception of time might be an illusion of our macroscopic world. At the fundamental level, the relationships between events may be far more complex and holistic than we imagine. So, why does this matter? It matters because it marks the boundary of human knowledge. Science has given us an incredibly powerful tool to predict the behavior of the universe, but it has not yet given us a definitive picture of what the universe is. It leaves us at a crossroads. Is reality a participatory process? Or is it a vast, branching multiverse? Or something else entirely? The answer defines not just the nature of the world, but our place within it. We began with a quiet assumption that the world ticks along just fine when we're not looking. Through the lens of quantum mechanics, we have seen that assumption challenged. The double-slit experiment showed us that the smallest bits of reality behave differently when watched. Schrödinger's cat took this idea to its logical conclusion, placing a creature in a state of quantum limbo, waiting for an observation to decide its fate. We are left standing before a fork in the road of reality. One path, the Copenhagen Interpretation, tells us that the universe is fundamentally probabilistic, a realm of potential that only becomes concrete through the act of measurement. It is a reality that seems to require an interaction to become definite. The other path, the many worlds interpretation, offers an escape from this, but at a staggering cost. It presents a cosmos that is constantly and infinitely branching, creating a separate reality for every possible outcome. In this vast multiverse, reality doesn't need us at all. It is complete, containing all possibilities, with our own lives being just one thread in an infinitely complex tapestry. The science is clear on the how the equations work. But the what reality truly is remains a quiet, unanswered question. Are we co-creators of the cosmos? Or are we passengers on one of an infinite number of timelines, unaware of the other versions of ourselves? The next time you close your eyes, wonder for a moment about the world you are no longer observing. Is it holding its breath, waiting for you to look again? Has it dissolved back into a shimmering sea of probability? The truth is, we don't know. And that uncertainty, that deep and thrilling mystery, is perhaps the most profound revelation of all. The universe is a ghost until you see it. Look at the world around you. Your screen, the room you're in, your own two hands. It all feels solid, real, permanent. It feels like it's just there. But what if I told you this solid, predictable reality is a grand illusion? What if everything you see, everything you touch, is just one possibility, plucked from an infinite number of ghosts? This isn't poetry. It's one of the deepest truths of modern science. The fundamental building blocks of your world, the very particles that make up you and everything you know, exist in a ghostly state of all possibilities at once. They are everywhere and nowhere. They are a haze of pure potential. And they only snap into the world you recognize, the single, solid reality you experience, when they are measured. When something, anything, looks. This suggests that observation isn't a passive act of just seeing what's there. It's an active process. It's the very thing that turns the ghost of potential into the fact of reality. And the key to this universe-altering secret lies in an experiment so simple, yet so profound. It has haunted and fascinated physicists for over a century. An experiment that shattered our picture of the universe, and our place in it, forever. The solid illusion. For most of human history, our universe was built on a simple, comforting foundation: common sense. A rock is a rock. It has a definite position. If you throw it, it follows a predictable path. If you turn your back on it, it doesn't vanish or morph into a wave of maybes. It stays a rock, right where it landed, waiting for you to look at it again. This is the world of classical physics, the world of Isaac Newton. It's a universe of certainty, of cause and effect, running like a magnificent, predictable clockwork machine. And this worldview is incredibly successful. It lets us build bridges that don't collapse and send spacecraft to distant planets with breathtaking accuracy. It's the physics of our everyday lives, and it works so well that for centuries, we had no reason to doubt it. We figured the universe, at all scales, behaved this way. We were just an audience in a grand cosmic theater, watching a play that would unfold the same way whether we were there or not. The moon is still there, we presumed, even when no one is looking at it. But at the turn of the 20th century, as scientists began to probe the very smallest pieces of matter, the realm of atoms and the particles inside them, they found that the rules of common sense just stopped applying. Down there, in the quantum realm, the universe quit behaving like a predictable machine and started looking like something far stranger, more ethereal, almost magical. It was a world where particles could be in multiple places at once. A world where they didn't have definite properties until they were measured. A world where the comforting solidity of reality dissolved into a mist of probabilities. This was so bizarre, so contrary to every intuition we have about how things should work, that it sparked a revolution. It introduced a fundamental mystery. Is the world really, out there, in a fixed state when we're not interacting with it? Or is the reality we see something we help conjure into existence? The clockwork universe was broken. In its place was a quantum ghost, and physicists needed to find a way to see it. That search led them to one of the most elegant and mind-bending experiments ever conceived. The experiment that changes everything. To understand how our view of reality was shattered, let's do a thought experiment. It's called the double-slit experiment, and its first version is incredibly simple and makes perfect sense. Imagine a wall with two thin, parallel slits cut into it. Behind this wall, you place a backstop, like a screen, that will show where things land. Now, let's say you stand in front of this setup and start firing paintballs, one by one, towards the slits. What pattern do you expect to see on the backstop? It's obvious, right? Some paintballs will hit the wall. Some will go through the left slit, and some will go through the right. Over time, the paintballs that make it through will create two distinct vertical bands on the backstop, pretty much shaped like the slits themselves. This is particle behavior. Each paintball is a solid little lump. It follows one path. It goes through one slit, not both. Simple. Now, let's reset the experiment. Instead of paintballs, let's imagine a tank of water in front of the wall. We create a ripple, a wave, that travels towards the slits. What happens now? The wave doesn't choose one slit. It approaches both at once. As the wave front passes through, it splits into two new, smaller waves. A moment later, these two new waves start to interact with each other. Where the crest of one meets the crest of another, they combine to make a bigger wave. Where a crest meets a trough, they cancel each other out. This is called interference. When this combined pattern hits the backstop, you don't get two bands. You get a series of alternating bright and dark stripes. A bright central band where the waves reinforced each other most, flanked by dark bands where they cancelled out, and so on. This is the signature of a wave. It happens because a wave can go through both slits at the same time and interfere with itself. So, we have two clear outcomes. Particles make two bands. Waves make a multi-band interference pattern. For a long time, this was the clear dividing line. An object was either a particle or a wave. It couldn't be both. But that was about to change. The quantum twist. Now, we get to the heart of it. Let's run the experiment one last time. We have our wall with two slits and our detector screen. But this time, we're going to fire something incredibly small. We're going to use an electron gun, firing single electrons, one by one, at the slits. An electron, as we're all taught, is a particle. It's a tiny speck of matter. So, based on our paintball experiment, we expect a clear result. The electrons will go through either the left slit or the right slit, and build up two distinct bands on the screen. We turn on the machine. Click. A single electron is fired. It makes a tiny dot on the detector. We can't tell which slit it went through, just where it landed. Click. Another electron, another dot. Click, click, click. We fire them one at a time, so there's no way they can interact with each other. For the first few dozen electrons, the pattern of dots looks completely random. But as we let the experiment run, firing thousands upon thousands of electrons, something impossible begins to happen. The random spray of dots isn't random at all. They're forming a pattern, and it is not the two-band pattern of particles. Instead, emerging from the static, clear as day, is an interference pattern. A central band, then a gap, then another band, then another gap. Let's be absolutely clear about how insane this is. These are the stripes of a wave. This is the pattern that should only be possible if something went through both slits at the same time and interfered with itself, just like the water wave. But we were firing single particles. We see their impact on the screen as a single, localized dot. How can a single particle, on its own journey, create a pattern that could only be formed by a wave going through both slits at once? The only conclusion, as bizarre as it sounds, is that the electron did exactly that. Each individual electron, between the gun and the screen, stopped being a simple particle. It became a wave of potential, a ghostly wave of probability. It didn't travel through the left slit or the right slit. It traveled through both at the same time. This unobserved electron existed as a field of possibilities that interfered with itself, dictating where it would probably land. The interference pattern is a probability map, showing us where the electron was most likely to materialize. This is the central mystery of quantum mechanics. The fundamental bits of our reality, when we are not looking, don't behave like solid objects. They act like ethereal waves of probability, spread out across space, holding all possible outcomes at once. The universe, at its core, is a ghost. The act of observation, The idea that a single particle goes through two places at once is so profoundly strange that the first, most natural response is, let's check. Let's find out which slit it really goes through. So, that's the next logical step. We need to peek. We modify the experiment by placing a tiny detector at the slits. Its only job is to register when an electron passes through. If it goes through the left slit, it'll go beep. If it goes through the right, it'll go boop. We aren't stopping the electron, just gathering a tiny bit of information about its path. Now we're ready. The detector is on. We start firing electrons again, one by one. Click. An electron is fired. We hear a asterisk beep. The left slit detector registered it. A dot appears on the backscreen. Okay, so that one went left. Click. Another electron. This time, a asterisk boop. The right slit detector fired. Another dot appears. That one went right. Click. Beep. Left. Click. Boop. Right. We do this for thousands of electrons. Each and every time, our detector gives us a clear answer. The electron went through one slit or the other. Never both. Mystery solved, right? It was just a normal particle all along. But then, we look at the pattern building up on the backstop screen. And the victory evaporates into pure shock. The interference pattern is gone. Completely vanished. In its place are two distinct vertical bands. Exactly like the paintballs. Let that sink in for a moment. The very act of finding out which path the electron took, forced it to behave like a simple, classical particle. It went from being a wave of possibility, spread across both slits, to a solid little thing that picked a single path. And all we did was look at it. This is the famous observer effect. The act of measurement, of gaining information, fundamentally changes the system being measured. Reality shifts depending on whether it is being watched. When unobserved, the electron is a ghost wave in a state of superposition, a mix of all possibilities. The moment the detector interacts with it, that cloud of probability, its wave function, seems to collapse. Out of all the possibilities, the act of observation forces reality to pick one. The electron is forced to make up its mind. The other possibilities don't just become hidden, they vanish. This is the core of what's known as the Copenhagen Interpretation, but it's important to know it's not the only idea out there. The collapse is one way to describe what's happening, but the mechanism behind it remains one of the biggest debates in physics. Some theories, like the many worlds interpretation, suggest the wave function never collapses at all, that all possibilities happen in branching parallel universes. But whatever the underlying reason, the experimental result is the same. The universe we see is not a fixed, pre-existing entity. It is a participatory process. What is an observer? This naturally leads to a deeply philosophical question. What, exactly, is an observer? For a while, some people, including a few physicists, flirted with the idea that human consciousness was the magic ingredient. It's a tantalizing thought, that the universe remains an undecided smear of probabilities until a conscious mind perceives it, solidifying reality. It's also, according to mainstream physics, almost certainly wrong. Through decades of experiments, the definition of observation has become much more mundane, yet just as profound. In quantum mechanics, an observer, or a measurement, doesn't need a mind or even eyeballs. An observation is simply any physical interaction that extracts information from a quantum system and records it in the wider world. Think about our detector at the slits. It might have worked by bouncing a single photon, a particle of light, off the electron. That photon then travels to a sensor, which records the event. That's the measurement. The electron's position is now known by another part of the universe. This interaction is enough to destroy the delicate quantum superposition. It's like trying to find a tiny ripple in a dark pond by throwing a rock at it. The splash might tell you where the ripple was, but in the process, you've completely destroyed it. Observation isn't passive, it's an invasive act. This is the heart of the framework developed by pioneers like Niels Bohr and Werner Heisenberg, who argued that the observer is simply the point where a quantum system interacts with a classical measuring device. That device, a photon, a detector, even an air molecule, creates an irreversible record of the interaction, and the ghostly quantum state becomes a concrete piece of information. So, you could set up the double-slit experiment with a detector, record the results to a hard drive, and only look at the data a year later. The interference pattern would still be gone. The collapse happened the moment the detector interacted with the electron, not when a human saw the results. This process, where the environment constantly interacts with quantum systems, is called decoherence. It's why we don't see quantum weirdness in our everyday lives. A macroscopic object, like a cat or a coffee cup, is so large it's being constantly measured by its environment trillions of times per second. Air molecules bombard it, photons bounce off it, the table pushes against it. Each interaction collapses its wave function instantly, pinning it to a single, definite reality. The ghost of a cat being in a superposition of both here and in the kitchen is vanquished by the first dust mote that touches it. Reality is not a static backdrop. It is a dynamic process born from interaction. Freezing reality, the quantum Zeno effect. The observer effect tells us that looking at a quantum system forces it to snap into a single state. But what if we took it a step further? What if we didn't just look once, but kept looking, over and over, in rapid succession? The result is a phenomenon called the quantum Zeno effect, and it basically says that if you watch a quantum system continuously, you can prevent it from ever changing. You can literally freeze reality just by observing it. The name comes from the ancient Greek philosopher Zeno of Elea and his arrow paradox, which argued that an arrow in flight can't really be moving. At any single, frozen instant, he reasoned, the arrow is in one specific place. If time is just a collection of these frozen instants, and the arrow isn't moving in any of them, how does it get to the target? While this was a philosophical puzzle for the Greeks, quantum mechanics turned it into a demonstrable physical reality. The principle is often summed up as, a watched pot never boils. In the quantum world, this is a literal truth. Imagine an unstable radioactive atom. It exists in a superposition of two states, its initial state and its final, decayed state. Over time, the probability of it decaying increases. But if we watch it by setting up a detector that constantly checks, has it decayed yet? How about now? Every measurement forces its wave function to collapse. If it hasn't decayed, our measurement forces it back into its initial, not decayed, state, resetting the clock on its decay process. If we make these measurements fast enough, we can effectively trap it. Each look nudges it back to the starting line before it has a chance to change. This has been experimentally verified. In one famous experiment, scientists took ultra-cold atoms that would normally tunnel or move from one position to another. By simply shining an imaging laser on them, by observing them frequently, they were able to suppress this movement. The atoms stayed put. The more they watched, the less the atoms moved. They froze the atom's motion through observation. The quantum Zeno effect is a powerful confirmation of the participatory nature of reality. It shows that observation isn't just a passive recording of events, it's an active intervention that can steer and even halt the flow of reality itself. Schrödinger's cat and the superposition of worlds. These concepts of superposition and collapse can feel incredibly abstract. So, in 1935, physicist Erwin Schrödinger devised a thought experiment to drag the sheer absurdity of these ideas into our world. His goal was to show what quantum mechanics would look like if applied to everyday objects, creating the most famous cat in science history. Imagine, Schrödinger said, you place a cat inside a sealed steel box. With the cat is a diabolical device, a single radioactive atom. This atom is quantum mechanical, So it exists in a superposition of having decayed and not having decayed. Let's say in 1 hour, there's a 50% chance it will decay. If the atom decays, it triggers a Geiger counter, which releases a hammer that smashes a vial of poison, killing the cat. If it doesn't decay, the cat lives. Now, seal the box and wait 1 hour. Without opening it, what is the state of the cat? Common sense says the cat is either alive or dead, we just don't know which. But according to the rules of quantum mechanics, the unobserved atom is in a ghostly superposition of both decayed and not decayed at the same time. And since the cat's fate is directly linked to the atom, the cat must also be in a superposition. It is not alive or dead. It is, in a very real physical sense, both alive and dead simultaneously. The ghost of the living cat and the ghost of the dead cat coexist in the box. It's only when we, the observer, open the box that we perform a measurement. In that instant, the superposition is broken. One of the interpretations is that the wave function collapses into one of two realities. We will find either a definitively alive cat or a definitively dead cat. But just before we looked, the universe had not yet made its choice. Schrödinger intended this as a paradox to show how ridiculous he thought this idea was. And yet, the thought experiment perfectly illustrates the core principles we see in the double-slit experiment. The unobserved electron is like the cat in the box, in a superposition of passing through both slits. Opening the box is like placing a detector at the slits. In both cases, the act of observation forces nature to abandon its ghostly ambiguity and commit to a single, concrete reality. The philosophical climax and implications. We've seen particles behave like waves until they're watched, seen observation freeze time, and contemplated a cat that is both alive and dead. These aren't just lab tricks, they are windows into the operating system of reality, with staggering implications. So, let's ask the ultimate question. Is the moon there when nobody is looking? If we were to strictly and perhaps a bit naively extend the quantum principle from a single particle to a giant object in isolation, the answer would be no, not in the solid way we think. The unobserved moon would be a vast cloud of probability, its wave function containing the potential for it to be in countless positions and states at once, a ghost moon. The moment a photon of light bounces off it and travels to your eye, a measurement is made, and this ghost snaps into the solid, cratered sphere we perceive. Of course, this feels absurd. And it is. We don't experience a flickering, ghostly world because of decoherence. The universe is a very noisy place. The moon is never truly unobserved. It is constantly being bombarded by photons from the sun, cosmic rays, and the gravitational pull of Earth. Every single one of these interactions is a measurement that collapses its wave function so rapidly and continuously that it is pinned into a classical, predictable state. Its ghostliness is wiped out trillions of times a second. This is the bridge between the bizarre quantum world and our solid classical reality. The weirdness is still there, underpinning everything, but it gets averaged out on large scales. But this doesn't diminish the core philosophical insight. It deepens it. Reality isn't a noun, it's a verb. It's a process, a continuous negotiation between potential and actuality, brokered by interaction. An object doesn't have definite properties on its own. Properties like position, or existence, or relational. They only come into being through interaction with something else. An electron only has a position when it interacts with a detector. The moon only has a definite location because it constantly interacts with the rest of the universe. The universe is not a collection of independent things. It is a web of relationships. Nothing exists in isolation. Without interaction, without measurement, the universe would remain an unwritten symphony, an ocean of pure, undefined potential. This journey into quantum mechanics can be deeply unsettling. It shakes the very foundation of what we call real. It transforms the universe from a static machine into a dynamic and participatory place. So, we want to ask you, how does this make you feel about your own reality? Does it feel less solid? More mysterious? Does the idea that the universe requires interaction to become real fill you with wonder or unease? Share your thoughts in the comments below. We're fascinated to know how this concept lands with you. And if your mind is blown and you want to keep questioning the nature of your reality with us, make sure to subscribe and hit that notification bell. We have so many more ghosts to explore. Conclusion. For centuries, science was a story of demystification. We learned we were small observers on a tiny rock in a vast, clockwork universe, discovering pre-written laws that would exist long after we were gone. We were just reading the pages of a book that was already finished. Quantum mechanics tears that story apart. It tells us something far more profound. The universe is not a finished book. It is a story being written, moment by moment, and we are not just its readers. We are among its co-authors. The very act of being part of the universe, of interacting with it, of measuring it, simply by existing as a collection of particles that bumps into other particles, is what helps transform the ghostly foam of potential into the concrete world we experience. Observation isn't just seeing, it's actualizing. You are not a passive spectator. You are part of the projector. Your interactions and the interactions of every other piece of matter and energy are the light that shines through the film of possibility, casting a single, sharp image onto the screen of reality. The universe doesn't need a conscious mind to be real, but it does need interaction. And you are a walking, breathing, thinking locus of trillions of interactions every second. You aren't just discovering reality. You are participating in its creation, every moment, just by being here. The ghost becomes real because you are here to see it. And that is the most astonishing reality of all. The experiment that accidentally broke reality. What if the world we perceive, the solid and dependable reality around us, is merely a surface? What if beneath it, the universe operates by a different set of principles, a deep and quiet strangeness it only reveals when not directly observed? This is not a premise for fiction, but the story of a real experiment. An experiment simple in its form, yet so profound in its results that it reshaped our most fundamental understanding of what is real. It is an inquiry that begins with a straightforward question but ends by calling into question the nature of existence itself. It suggests the universe possesses a different character when unobserved, a ghostly state of possibility that resolves into fact only through the act of interaction. We are about to begin a journey to the very heart of quantum mechanics, to what is arguably the single most important and most unsettling experiment ever designed. It is an experiment that left us not with simple answers, but with a deeper question. What is the nature of reality? This is the story of how firing single particles at two tiny slits revealed that the universe we thought we knew was an incomplete picture. The world as we know it, the classical view. Before we explore this new territory, we must first establish the ground on which our classical understanding was built. For centuries, our view of the cosmos was shaped by classical mechanics. This is the universe of Isaac Newton, a predictable and orderly system. The idea was both simple and comforting. Everything, from an object in motion to the orbits of planets, followed laws that were knowable and absolute. If one knew the position and momentum of an object, one could, in principle, calculate its entire future. The universe was seen as a grand, deterministic machine. An object was an object. It was solid, it possessed a definite location, and it could only be in one place at any given time. This forms the foundation of our everyday intuition. Let us construct a model of this reality. Imagine a wall with two thin, parallel slits cut into it. Now, imagine using a device that fires small projectiles, like paintballs, randomly toward that wall. What pattern would we expect to see on a screen placed behind it? The result is intuitive. Some projectiles will strike the wall. Others will pass through the left slit, and some will pass through the right. On the screen, we would find two distinct vertical bands of paint, each a direct impression of the slit it passed through. If one slit is closed, one band appears. The final pattern is simply the sum of the particles that went through each individual slit. Each projectile follows its own single, definite path. It travels through either the left slit or the right. It cannot do both. This is the world as we experience it, a reality that seems solid and predictable. This is our baseline. For a long time, this was thought to be the complete story. The universe was understood as a collection of these projectiles, merely at a much smaller scale. Atoms, electrons, all the fundamental components of matter, were assumed to be nothing more than incredibly small, solid objects. It was logical to assume that if we were to scale down our experiment to the level of these particles, the result would be identical. Firing the smallest bullets imaginable at two slits should produce two lines on a detector. It is intuitive, and, as science was about to discover, it is fundamentally wrong. The first anomaly, firing the tiniest particles. The story of how we found the first departure from this view begins not with particles, but with waves. Long before we could manipulate single electrons, scientists were debating the nature of light. In the early 1800s, the English polymath Thomas Young designed an experiment to contribute to this debate. He directed a beam of light at a barrier with two thin slits, much like our earlier setup. Light, however, did not behave like projectiles. Instead of two sharp lines, Young observed something unexpected: a pattern of alternating bright and dark bands spreading across the screen. This is known as an interference pattern. To understand this, we change our analogy from projectiles to waves on the surface of a pond. If two pebbles are dropped into calm water, each creates expanding ripples. Where these ripples meet, they interfere. In some places, the crest of one wave aligns with the crest of another, creating a larger wave, constructive interference. In other places, a crest meets a trough, and they cancel each other, leaving the water flat, destructive interference. Thomas Young realized this was precisely what was happening with light. It was behaving like a wave. The wave passed through both slits at once, creating two new wave fronts that interfered with each other. The bright bands were areas of constructive interference. The dark bands were areas of destructive interference. With this experiment, Young seemed to prove that light was a wave. For a century, this was the accepted view. Then came the 20th century. Physicists like Max Planck and Albert Einstein showed that light also behaved as if it were composed of discrete packets of energy, which they named quanta, and which we now call photons. Furthermore, in 1927, Davison and Germer demonstrated that electrons, once considered the quintessential particles, also exhibited wave-like properties. This led to a new question. What would happen if Young's double-slit experiment were performed not with a continuous beam, but with these discrete particles, like electrons, fired one at a time? This is where our familiar reality begins to diverge. Imagine our setup once more. An electron gun fires a single electron. It travels toward the wall with two slits, and a detector screen behind it records where the electron arrives. If an electron is a particle, the outcome seems clear. It will go through one slit or the other. After we fire thousands of electrons, one by one, we should see the familiar pattern: two distinct lines. There is no continuous wave, and nothing for a single electron to interfere with. So, the experiment was performed. The apparatus was turned on. The first electron is fired. It travels through the setup, and a single point of light appears on the detector. A definite position. So far, it looks like a particle. Another electron is fired, and another point appears in a different location. This is repeated for thousands upon thousands of individual electrons, each making its own separate journey. But as these points accumulate, an unexpected form begins to emerge. Slowly, a pattern takes shape. It is not two lines. It is the interference pattern, the same arrangement of alternating bands that Thomas Young saw with waves. The electrons were sent one at a time. Each made the journey alone. Yet, they collectively arranged themselves into a pattern that could only be formed if each electron had passed through both slits simultaneously and interfered with itself. How can a single, indivisible entity pass through two separate openings at once? It defies our classical understanding of an object. The particles were behaving like waves. This result was not merely a curiosity, it was a profound break with the classical view of reality. The universe, at its most fundamental level, was not operating by the rules we had assumed. A deepening mystery, the particle wave. This result gave rise to a central concept in quantum mechanics: wave-particle duality. In the quantum realm, entities are not strictly particles or waves. They exhibit properties of both. An electron, a photon, or even a whole atom can behave like a localized particle in one context, and a spread-out, interfering wave in another. To describe this, physicists developed a new mathematical framework, the wave function. As formulated by Erwin Schrödinger, the wave function describes a quantum object not by a definite position, but by a field of all its potential positions. Before an electron arrives at the detector, it does not have a single location. It exists as a probability wave, a distribution of possibilities. In the context of the double-slit experiment, when this probability wave encounters the barrier, it does what any wave would do. It passes through both slits. These two new probability waves then propagate forward and interfere. Where the waves constructively interfere, there is a high probability of finding the electron. Where they destructively interfere, there is a low or zero probability. When we fire a single electron, it exists as this wave of potential. It goes through both slits because its field of possibility includes both paths. Then, upon interacting with the detector screen, this wave of potential disappears, and the electron materializes at a single point. The location it materializes in is random, but the probability of it choosing any given spot is governed by the interference pattern of its wave function. Over time, as thousands of electrons complete this journey, they collectively map out these probabilities. They land most often in the high probability regions and never in the zero probability regions. The interference pattern is not built by electrons interacting with each other. It is the statistical result of thousands of individual probability waves collapsing, one by one. This concept forces us to abandon the idea that objects possess definite properties independent of measurement. Quantum mechanics suggests that reality at this level is probabilistic. An unobserved particle is not a small object with a hidden location. It is a smear of potential, a wave function representing a range of possible outcomes. It only acquires a definite position at the moment of interaction. As the physicist Richard Feynman stated, the double-slit experiment holds the central mystery of quantum mechanics, a phenomenon, impossible, absolutely impossible, to explain in any classical way. And the mystery was about to deepen. The investigation, the act of observation. Faced with this paradox, scientists posed the next logical question. What if we simply watch to see which path each electron takes? The plan was to place a detector at the slits themselves, one that could register which slit each electron passed through. The setup was modified. The electron gun, the barrier, and the backscreen remained, but a which path detector was added at the slits. As an electron passed through, this detector would signal its path, left slit or right slit. At last, the ambiguity would be resolved. The experiment began. The electron gun was activated, as were the new detectors. The first electron is fired. The detector at the left slit signals its passage. The electron continues to the backscreen and makes a dot. Another electron is fired. This time, the right slit detector signals. It hits the screen. Another dot. This was repeated thousands of times. For every single electron, the detectors worked, confirming exactly which path was taken. There was no ambiguity. As classical intuition suggested, each electron went through one slit or the other, never both. Sanity, it seemed, was restored. All that remained was to look at the final pattern on the back screen, which should now consist of two simple lines, matching the behavior of projectiles. But what they saw was the culmination of this story. The interference pattern was gone. Completely. In its place were two distinct lines, the exact pattern produced by projectiles. The only difference in the experiment was the act of observation. When the electrons were not watched, they behaved as waves, passing through both slits to create an interference pattern. The moment their path was measured, they behaved as particles, choosing a single slit and producing a two-line pattern. The outcome was contingent on the act of measurement. It seemed as if the universe's behavior changed depending on whether it was being observed. The observation itself altered the result. This discovery was so profound it felt as if the very foundations of physics were shifting. The observer effect, a deeper look. This phenomenon became known as the observer effect. It is the principle that the act of measuring a system inherently disturbs it. It is crucial, however, to understand what observer and measurement mean in this context. The observer does not need to be a conscious being. The term has nothing to do with consciousness. The observer is the detector. The act of measurement is a physical interaction. To know which slit the electron went through, the detector must interact with it, for example, by bouncing a photon off of it. That photon carries away information about the electron's position. But in that act, the photon also imparts a small amount of momentum to the electron, a kick. This physical interaction is the key. Before the measurement, the electron exists as a spread-out probability wave, able to interfere with itself. But the kick from the measurement interaction is enough to destroy the delicate coherence of that wave. It forces the wave of possibilities to collapse into a single, definite reality, a particle at a specific location, on a specific path. This is not just a theory. An experiment at the Weizmann Institute of Science in 1998 used a which-path detector whose interaction strength could be varied. When the detector was off, a clear interference pattern appeared. When it was on at maximum strength, the pattern vanished, leaving two lines. But when the detector was set to be very weak, providing only partial information about the path, a faint, low-contrast interference pattern emerged. The more which path information was gained, the more the wave-like interference was diminished. It was a trade-off. This brings us to another cornerstone of quantum mechanics, Werner Heisenberg's uncertainty principle. Formulated in 1927, it states that there are pairs of properties of a particle, such as its position and its momentum, that cannot be known with perfect, simultaneous accuracy. To produce an interference pattern, the electron's wave must be spread out, meaning its position is uncertain, it could be at either slit. But when we use a detector to determine its position, we disturb its momentum. That disturbance scrambles the wave information. A fundamental trade-off is enforced. Gaining information about its particle-like property, path, results in losing information about its wave-like property, interference. One can know the path the particle took, or one can observe the interference pattern it creates, but one cannot do both at the same time. These ideas challenge our deepest intuitions about the world. The greatest minds in physics spent decades debating their meaning. But they also provide a window into the true, and quieter, strangeness of reality. We are only just beginning this exploration. If you wish to continue this journey into the nature of the universe with us, consider subscribing to follow our future inquiries. The philosophical implications, the nature of reality. The double-slit experiment does more than just describe the behavior of particles. It leads us to profound philosophical questions about the nature of reality itself. If an electron only solidifies into a particle when measured, what is it when we are not looking? The most common framework for this is the Copenhagen Interpretation, developed by Niels Bohr and Werner Heisenberg. In its starkest form, it suggests that properties like position simply do not exist until they are measured. Before measurement, the electron is in a superposition, a blend of all possibilities described by its wave function. The act of measurement compels this field of potential to resolve into a single, definite outcome. This is a radical departure from the classical view. It suggests that reality, at its base, is not deterministic, but probabilistic. The universe is not a collection of objects with pre-existing properties, but a dance of potentialities that become concrete only through interaction. Albert Einstein found this idea difficult to accept, arguing that our quantum description must be incomplete. He famously asked a colleague if he really believed the moon exists only when he is looking at it. From the Copenhagen perspective, the question is not absurd. An unobserved moon, like an unobserved electron, exists as a wave function of probabilities. For a macroscopic object like the moon, these probabilities are so overwhelmingly concentrated in one place that the distinction is functionally meaningless. At the quantum level, however, the distinction is everything. This is not the only interpretation. The many worlds interpretation proposes that the wave function never collapses. Instead, at every quantum measurement, the universe branches. In one universe, the electron is measured going through the left slit. In another, parallel universe, it is measured going through the right. Both outcomes occur and are equally real. We simply experience only one of these branches. There is no scientific consensus on which interpretation is correct. They are different frameworks we use to make sense of the same quantum facts. Conclusion: the double-slit experiment began as an inquiry into the nature of light and matter. It was not designed to reshape our perception of the cosmos, but through its paradoxical results, it did just that. It did not break reality, but it did reveal that our classical, intuitive assumptions about reality were an incomplete picture. It showed us a universe far stranger and more subtle than we had imagined. A universe where particles can be waves, and where the act of observation is an active participation in determining what is real. The physical disturbance of measurement is what erodes the interference, not a mystical consciousness. We learned that at its smallest scales, the universe does not seem to deal in certainties but in probabilities. The solid, definite world of our everyday lives emerges as a large-scale average from a hazy and uncertain quantum foundation. The double-slit experiment does not provide final answers. Its true legacy is the opposite. It is a generator of questions. It leaves us to contemplate one of the deepest mysteries in all of science. A question we continue to explore today. What is the true nature of reality? And does the world we know exist in the same way when it is not being observed? You are deleting reality by observing it. We tend to think of ourselves as quiet witnesses to the world. That when we look at a tree, a screen, or the moon in the night sky, we are simply receiving information from a reality that exists separately from us. It is the most natural assumption we make. That the world is out there, and we are in here, looking out. For a century, quantum mechanics has been gently questioning this assumption. You may have heard of the observer effect, the idea that the act of looking at something changes it. It is often presented as a mysterious process, where reality waits for our attention before it settles into a final form. But what if that is not the complete story? What if that story has something backward? What if a different perspective in physics suggests that our simple act of observation isn't creating reality, but is in fact simplifying it? That before we look, the universe exists in a state of immense complexity, and that our glance, our measurement, our simple act of knowing, encourages it to present one single, definite state. This is not a story about consciousness magically creating the world. It is a story about how our perception might be methodically filtering out what is truly there. We are about to take a journey to the edge of modern quantum thought, where physicists are considering a quiet possibility that the unobserved universe is not a vague fog, but a realm of near infinite information. And every time we look, we are the ones choosing which piece of that information to see. Think of the most intricate thing you can imagine: a sprawling forest ecosystem, a vibrant coral reef, an infinitely detailed fractal pattern. Now, imagine that with a single glance, you could perceive that entire, complex reality as just one of its single, uniform colors. Simple, devoid of its prior richness. This is a power you might be using every second of every day without even knowing it. This is the story of how observing the universe may not be bringing it into focus, but might be leaving most of its information behind. The quantum riddle and the old story of observation. To understand this idea, we first need to revisit the place where this puzzle began 100 years ago, the double-slit experiment. It is the origin story of all quantum uncertainty, and it's where the observer first appeared and quietly changed everything. The setup is simple. There is a barrier with two vertical slits in it. We can fire things at it. Let's say, tiny pellets, like grains of sand. On the other side, a screen records where each pellet lands. As you would expect, two distinct bands appear on the screen, right behind each slit. Some pellets go through the left, some go through the right. It is simple, classical, and makes perfect sense. But when physicists tried this with the fundamental parts of our world, things like electrons, something quietly strange happened. When they sent electrons one by one at the two slits, they did not get two bands. Instead, they got a complex pattern of many bands, an interference pattern. This is the signature of a wave. Think of dropping two stones into a pond. The ripples from each spread out and interact. Where two crests meet, they create a bigger wave. Where a crest and a trough meet, they cancel out. The pattern seen in the experiment is precisely this. Areas where many electrons landed, and areas where almost none did. This result is profoundly strange. It implies that each electron traveling alone somehow passed through both slits at the same time, like a wave, and interfered with itself before arriving at the screen. The electron was not a particle in the classical sense. It was a wave of possibility that only resolved into a definite location when it reached the detector. This is where the observer enters the story. Physicists, understandably puzzled, decided to watch which slit each electron went through. They placed a detector at one of the slits to gain information about the electron's path. And this is where reality seemed to shift. The moment they observed which slit the electron passed through, the interference pattern vanished. The electrons stopped behaving like waves and started acting like simple grains of sand again. The screen showed just two bands. It was as if the act of being measured changed the electron's behavior. This is the famous observer effect. The very act of measurement, of gaining information about the electron's path, seemed to cause it to choose a single state. It collapsed from a wave of many possibilities into a particle with one definite history. This led to the first major attempt to explain the quantum world, the Copenhagen Interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s. Their conclusion was as subtle as it was unsettling. Properties of a quantum system, like an electron's position, simply do not have a definite reality before they are measured. The unobserved electron isn't in one place or another, it exists in a superposition of all its possible states at once. Observation doesn't just disturb what was there. It seems to participate in selecting the definite outcome from a haze of potential. For Albert Einstein, this was difficult to accept. He argued for an objective reality that exists independent of us. He once asked a biographer, "Do you really believe the moon exists only when you look at it?" For Einstein, the moon was obviously there, whether anyone was observing it or not. The Copenhagen Interpretation, however, seemed to suggest that, at the quantum level, the answer was a quiet no. Before observation, there is no definite moon, there is only a probability wave of moonness. This interpretation, while commonly taught, has always carried a central mystery, the measurement problem. What exactly counts as an observation? Does it require a conscious human? Or is any physical interaction enough? The line between the quantum system and the classical world of observers seemed arbitrary. Where does the quantum fuzziness end and the concrete reality we experience begin? This question led to even deeper paradoxes. The most famous of these is Schrödinger's cat. Imagine a cat in a sealed box. Inside is a single radioactive atom. A detector is set up to trigger a hammer that will release poison if the atom decays, and the cat will perish. The atom's decay is a quantum event. According to the Copenhagen Interpretation, the atom, after a time, is in a superposition of both decayed and not decayed. But because the cat's fate is linked to the atom, the entire system inside the box is also in a superposition. The cat is not dead or alive. In a physical sense, it is described as being both dead and alive simultaneously. It is only when an observer opens the box and looks inside that this superposition collapses into one of the two definite realities. Schrödinger designed this thought experiment to show how strange it was to apply these rules to the large-scale world. A cat cannot be both dead and alive. But the mathematics of quantum mechanics suggested it could be. This highlights the measurement problem in its most dramatic form. What is so special about the act of opening the box? This leads us to an even more profound thought experiment, Wigner's friend. It takes Schrödinger's cat one step further, and puts the observer themselves inside the box. The paradox deepens when observers disagree on reality. The Wigner's friend paradox, proposed by Nobel laureate Eugene Wigner in 1961, exposes the quiet contradictions that can arise from the Copenhagen interpretation. It asks a simple question: what happens when you observe an observer? Imagine a scientist, the friend, inside an isolated laboratory. Her job is to perform a quantum measurement, for instance, determining if a photon's polarization is horizontal or vertical. According to quantum mechanics, before she measures it, the photon is in a superposition of both states. The friend performs the measurement. From her perspective, the superposition collapses. She sees a definite result, let's say, horizontal, and records it. For her, inside the lab, reality has settled into a single, concrete state. But now, let's consider the perspective of another scientist, Wigner, standing outside the sealed laboratory. From his point of view, he has no information about what happened inside. For him, the entire laboratory, the friend, her equipment, her notebook, the photon, is one large, unobserved quantum system. Just as the cat became entangled with the atom, the friend has now become entangled with the photon. Because the photon was in a superposition, the friend, from Wigner's perspective, must also be in a superposition. There is a version of the friend who saw horizontal, and a version who saw vertical. Wigner must describe the lab's contents as a single, large wave function. A superposition of friend who saw horizontal, and friend who saw vertical. So we arrive at a quiet disagreement. The friend, inside the lab, believes a definite measurement occurred at 12:01 p.m. Wigner, outside, insists that no collapse has occurred, and that the friend herself is in a quantum superposition. He believes the collapse only happens later, when he opens the door and asks his friend what she saw. Who is right? According to the standard rules, both of them are. This paradox reveals that the Copenhagen interpretation can lead to a situation where two observers have different, equally valid descriptions of reality. One sees a definite fact, the other sees a cloud of possibilities. For years, this was treated as a philosophical puzzle. But in recent times, beginning around 2019, physicists have performed real-world experiments that confirm the core strangeness of the Wigner's friend scenario. Using entangled photons as stand-ins for the friends, They have shown that it's possible to create situations where our basic assumptions about reality, like the idea that a measurement has a single, objective outcome, are violated. These experiments suggest that there may be no such thing as an absolute, objective fact. A fact might only be a fact relative to an observer. This is the quiet puzzle that a century of quantum mechanics has led us to. A world of fuzzy probabilities, dead and alive cats, and observers who cannot agree on what has happened. It seemed that the more we tried to pin reality down, the more it slipped through our fingers. For a long time, this is where the story paused. The paradoxes of measurement seemed to be a fundamental part of the theory. Physicists were often encouraged to focus on the calculations, because the equations worked, even if no one was sure what they meant. The dominant story remained that observation somehow brings a definite reality out of a probabilistic fog. But now, some physicists are challenging this old story. They suggest we have been looking at the entire process from the wrong direction. They suggest the paradoxes arise not because reality is undefined before we look, but because we have misunderstood what our act of observation truly does. The new perspective: observation as selection. This is where our story takes a different path. This new perspective, explored by physicists like Vlatko, proposes a gentle reimagining of the universe. Instead of thinking that observation creates reality, this view suggests that reality is always fully real, but that observation limits what we see of it. It argues that the unobserved universe is not a realm of hazy uncertainty, but one of maximum information. To grasp this, it can be helpful to think about two kinds of information. We can call them C numbers and Q numbers. These are not standard terms, but they are a useful way to think about the ideas Vedral and others are exploring. A C number is a classical number, the kind we use every day. A single, definite value. It is simple, concrete, and contains a limited amount of information. This is the world of classical physics. A Q number, or quantum number, is something much richer. It is not a single value. A Q number can be thought of as containing information about all the possible states of a system at once, along with the relationships between them. It describes the full wave of possibility. The key insight of this view is that this Q number is the reality. An electron's real, physical state is this entire structure of information. Think of it this way. In the classical world, if you lose your keys, they are in a definite location. You just do not know it. In the Copenhagen view, the keys aren't anywhere until you find them. In this newer, Q number, perspective, the key's true state is a complete description of all possible locations at once. The physical reality of the keys is this entire web of possibilities. With this idea, let's look again at the universe. This perspective argues that the fundamental reality of the universe is described by Q numbers. Reality is made of these incredibly rich, multifaceted informational structures. The unobserved universe is a world humming with an immense density of information. The universe, when you are not looking at it, is in its most complete and detailed state. So what happens when you observe it? Here is the quiet twist. Observation is the process of taking a rich, complex Q number and extracting from it a single, simple C number. When your measuring device interacts with an electron, it cannot process the entire web of information that is the electron's true state. A classical instrument, by its nature, can only register a single outcome. It's like trying to describe a complex painting by giving only its average color. You ask the system a simple question, and its Q number, which contains the information about everywhere at once, is encouraged to provide a single C number. Here, the act of measurement is an act of informational selection. It is a translation from a rich quantum language to a simple classical one. And in that translation, much of the information is left behind. Let's go back to our analogy of an intricate fractal pattern. The fractal is the Q number, the true, unobserved state of the system. Your observation is like looking at it with a device that can only see one color. The device registers blue and reports that the reality is blue. It is not wrong. There was blue in the fractal, but it has missed the infinitely complex picture. In asking the system a simple classical question, you have effectively filtered out all the other information that constituted its true reality. This reframes the observer effect. Observation is not a mystical creation of reality from nothing. It is an interaction that simplifies what we perceive of reality. The universe, in this view, is always something far richer, and our observation is what makes it appear simple. This also provides a different lens through which to view Heisenberg's uncertainty principle. The principle states that you cannot simultaneously know with perfect accuracy certain pairs of properties, like a particle's position and its momentum. In the old view, this was because reality itself was uncertain. In this new view, it is a direct consequence of your act of selection. When you ask the particle's Q number for a very precise C number for its position, you do so by leaving behind the information related to its momentum. The more information you request about one property, the more information about its complementary property is lost in the translation to the classical world. The uncertainty isn't in the reality. It is a fundamental limit on how much of that reality can be captured in a single, classical description. This perspective offers a potential way out of the paradoxes that have troubled quantum mechanics. It suggests we do not live in a half-real world. We live in a world of profound, hidden complexity, and we have been mistaking our limited, classical view for the whole picture. A universe of lost information and dissolving paradoxes. So, what does this observation as selection framework do to the paradoxes of Schrödinger's cat and Wigner's friend? It doesn't so much solve them as it dissolves them, by showing they were based on a challenging premise. Let's revisit Wigner's friend. Remember the disagreement. The friend inside the lab says reality collapsed at 12:01 p.m., while Wigner outside says the entire lab is in a superposition. In the Q number view, the contradiction fades. When the friend measures the photon, her brain and equipment become entangled with the photon's Q number. The entire system of friend plus lab plus photon evolves into a new, more complex Q number. No information has been lost. From her own perspective, she has formed a correlation, a classical memory, a C number, that says horizontal, but the total reality still contains all possibilities. From Wigner's perspective outside, his description of the lab as a single, complex Q number is perfectly correct. There is no contradiction because both observers are describing the same underlying quantum reality, just from different levels of inclusion. The friend is describing a correlation within the system. Wigner is describing the total system itself. The paradox only arose because we were focused on the idea of collapse. We assumed a collapse must happen at a definite time and destroy other possibilities. But in this view, the other possibilities are never destroyed. They just become part of a larger, entangled state. What we call collapse is just the moment a C number, a piece of classical information, is extracted by an observer for their own use. This offers one possible resolution, though it is one of several competing ideas. Interpretations like the many worlds theory or cubism also provide ways to think about these problems, and the discussion among physicists is far from settled. But this perspective is compelling because it seeks to unify the quantum and classical worlds with a quiet elegance. It suggests there is one quantum reality, and our classical world is just the sliver of it that we are able to access. This leads to a profound shift in how we see our place in the cosmos. Einstein's question about the moon gets an even more interesting answer. Does the moon exist when no one is looking? Yes. And it is more complex, more informationally rich than the simple rock you see. The unobserved moon is a magnificent Q number, a reality containing the superposition of every possible position, every possible temperature, all held in perfect quantum coherence. When you look at it, your observation selects from that symphony of possibility a single, clear note. You receive a C number, a white-gray sphere at a specific location. You have just experienced the classical moon, a simplified representation of the true quantum moon. This idea, that the universe's fundamental currency is quantum information, is sometimes called it from qubit. The implications are quiet but staggering. If observation is selection, it means the universe is at its most complete when we are not looking. This gently flips the anthropic principle on its head. Instead of the universe being fine-tuned for our existence is a process that constantly simplifies the universe's true state by filtering it through our limited classical perception. What if our minds are exquisitely evolved to take the immense complexity of the quantum world and compress it into a single, stable, classical story so that we can survive? The feeling of a solid table under your hand is not a direct perception of its true quantum state, but a heavily processed, classical output. Your brain has filtered out the quantum fizz of probabilities and given you a simple, useful C number, solid. This journey into the heart of quantum mechanics began with a simple question about what happens when we look at things. We started with the familiar story of the observer effect, where looking at something brings it into being. We saw how this idea led to quiet paradoxes like Schrödinger's cat and Wigner's friend. But then we explored a different perspective that turns this story around. A view where the universe, left to itself, is a place of immense information and complexity. A reality described not by simple facts, but by rich quantum structures that contain all possibilities at once. From this viewpoint, our role as observers is one of selection. Every glance, every measurement, is an act of simplification. We trade richness for a single, definite fact. We have traveled from a simple experiment with two slits to the quiet possibility that our perception simplifies the world around us. If this kind of exploration helps you see the world a little differently, consider liking the video and subscribing to the channel. So, the next time you look up at the night sky and see the moon, take a moment to consider what might be happening. The old story told you that your gaze was what made the moon real. But this new story, whispered at the frontiers of physics, suggests something far more humbling. It suggests that before you looked, the moon was an entity of unimaginable quantum complexity. And in the instant you perceived it as a simple, silver disk, you may have just experienced one piece of a much larger story. What if the true richness of reality is not in what we see, but in all the information we leave behind in the act of seeing? The question is no longer whether a tree makes a sound if no one is there to hear it. The new question is, what symphony did we quiet, just by showing up to listen? Science proves the universe is just a game of chance. Long before our world of solid objects and predictable outcomes took shape in our minds, the universe was already experimenting. It existed as a haze of infinite possibilities, a ghostly fog of maybes. What if the very fabric of existence only snaps into a definite reality when it is observed? This is not a thought experiment, but the profound and deeply unsettling picture painted by our most successful theory of the physical world, quantum mechanics. The universe, at its most fundamental level, appears to be in a ghostly state of all possibilities at once, and it only decides what is real when an observation is made. This idea shatters our most basic intuitions. We navigate a world of solid objects, of causes and effects, of a past that is fixed and a future yet to come. But a century of mind-bending experiments has compelled us to confront a new reality, one that is not as solid as it seems. It is, perhaps, a cosmic game of chance, where the rules are written in the language of probability, and the outcome is never certain until the result is seen. This is a journey to the very edge of what is real. We will dismantle the solid world of our intuition, piece by piece, and rebuild it according to the bizarre rules of the quantum realm. We will unpack the scientific evidence that suggests our universe behaves like a grand game of chance. First, we will confront the most famous experiment in science, the double-slit experiment, a test that reveals the dual identity of everything in existence. Then, we will explore the concept of superposition, this ghostly state of being everything at once, and meet Schrödinger's unfortunate cat, a creature trapped between life and death. And finally, we will grapple with the deepest mystery, the observer. What does it mean to look? And if reality is governed by probability, who or what is rolling the dice? The solid world that isn't, the illusion of certainty. Our everyday experience suggests that the world is solid, predictable, and real. When a ball is dropped, it falls. We can know its path and where it will land. This is the world of classical physics, a masterpiece of human intellect built by titans like Isaac Newton. For centuries, this framework was our guide to the cosmos. It gave us laws of motion and universal gravitation, allowing for the prediction of planetary orbits with breathtaking accuracy. The universe, in this view, was a magnificent clockwork machine. If one knew the position and momentum of every particle, one could, in principle, calculate the entire past and future of the cosmos. Everything was determined. There was no room for chance. This classical view is deeply intuitive. It matches what we see and feel. A chair possesses a definite location and definite properties. It does not flicker in and out of existence or exist in a ghostly state of being both a chair and not a chair. It is simply there. We build our lives on this foundation of objective reality. But this intuition, however powerful, is born of an illusion of scale. The solid objects we interact with are not truly solid. They are composed of trillions of atoms, and atoms are notoriously full of empty space. An atom is a tiny, dense nucleus surrounded by a vast cloud of electrons. If an atom's nucleus were scaled to the size of a marble, its electron cloud would extend for roughly 100 meters in every direction. The feeling of solidity is not solid particles bumping into solid particles. It is the electromagnetic repulsion between the electron clouds of your hand and the table. You have never truly touched anything in your life. This emptiness is the first clue that our classical intuition is in trouble. But the true strangeness begins when we probe the behavior of the particles that inhabit this void. As scientists of the early 20th century began this work, the clockwork universe of Newton started to break down. They discovered a world that was not deterministic, but probabilistic. A world where particles could be in multiple places at once. A world where the simple act of looking at something could change what was there. The solid, predictable reality we thought we lived in was merely a macroscopic approximation. Beneath the surface, the rules were different. The game was one of chance, not certainty. And the experiment that first revealed this shocking truth is one of the most elegant in the history of science. The double-slit experiment. Reality's greatest magic trick. Imagine a wall with two narrow slits, and a device that can fire tiny objects, one by one. On the other side, a detector screen records where each object lands. This is the double-slit experiment, a test so fundamental that physicist Richard Feynman said it contains the central mystery of quantum mechanics. First, consider this experiment with marbles. As you fire them one at a time, some pass through one of the two slits. On the detector screen, you find two distinct bands of hits, directly behind each slit. This is logical. Each marble is a particle. It goes through either the left or the right slit and lands accordingly. Now, let us swap the marbles for waves. In a tank of water, ripples approach the slitted wall, pass through both slits simultaneously, and spread out. The two new sets of waves interfere with each other. Where crests meet, they create a bigger wave. Where a crest meets a trough, they cancel out. On the back wall, you see not two bands, but many, an interference pattern, the unmistakable signature of a wave. So, we have two clear outcomes. Particles create two bands, while waves create an interference pattern. Now, reality begins to unravel. We return to our device, but this time, we fire electrons, the tiny particles that constitute matter. We fire them one by one, like the marbles. We expect to see two bands. Instead, as millions of electrons hit the screen, a breathtaking and impossible pattern emerges. It is not two bands. It is an interference pattern. The electrons, fired one at a time, are behaving like waves. This is profoundly strange. How can a single particle create a pattern that requires interference? It implies that something is going through both slits at once and interfering with itself. It is as if each electron becomes a wave of possibility, a probability wave, that passes through both slits simultaneously. Only when it hits the detector does this wave collapse, and the electron's position is recorded at a single point. The electron did not go through the left slit or the right slit. In a very real sense, it went through both. This seems impossible. So, scientists decided to check. They placed a tiny detector by the slits to register which slit each electron passed through. Now, the detector tells us, this one went through the left slit, or, this one went through the right slit. And here, the universe plays its ultimate trump card. The moment you turn on the detector to observe which slit the electron goes through, the interference pattern vanishes. The pattern on the screen reverts to the simple, two-band pattern of the marbles. The very act of measuring which path the electron took forced it to behave like a particle. When you do not look, the electron is a wave of potential passing through both slits. When you do look, it is a particle passing through only one. This is the observer effect. The outcome changes depending on whether we are watching. It is as if reality exists in a ghostly state of all possibilities, and only commits to a single, concrete state when it is measured. Our observation seems to be an intrinsic part of what makes that reality concrete. Superposition and the wave function, the ghostly state of all possibilities. The behavior of the electron in the double-slit experiment is not an exception, it is the rule. This state of existing in multiple possibilities at once is a fundamental principle of quantum mechanics known as asterisk superposition. Before a measurement is made, a quantum system, an electron, a photon, an atom, does not possess definite properties. It exists in a weighted combination of all its possible states simultaneously. Physicists describe this state of potential using a mathematical tool called the asterisk wave function asterisk, represented by the Greek letter psi. The wave function is the heart of quantum mechanics. It does not tell you where a particle is. It tells you the asterisk probability of finding the particle at any given location. It is a wave of pure probability. The electron in the double-slit experiment, before it is observed, is its wave function, a cloud of possibilities spread out in space. When an observation occurs, when the electron hits the screen, or a detector checks its path, the wave function, once spread out, instantaneously changes. It collapses into a single, sharp spike. Out of all potential realities, one becomes actual. This is asterisk wave function collapse. The final interference pattern is the statistical map of all these individual, probabilistic collapse events. This concept is so counterintuitive that Erwin Schrödinger, a pioneer of quantum theory, devised a thought experiment to illustrate its absurdity when applied to our world. This is the story of Schrödinger's cat. Imagine a cat in a sealed box with a device containing a single radioactive atom. The atom is in a superposition. Over 1 hour, it has a 50% chance of decaying and a 50% chance of not decaying. If the atom decays, it triggers a mechanism that releases a poison, killing the cat. If it does not decay, the cat lives. After 1 hour, the atom is in a superposition of both decayed and undecayed states. Because the cat's fate is entangled with the atom, the cat itself must also be in a superposition. According to a literal reading of the quantum math, the cat is simultaneously alive and dead. It is only when we open the box, make an observation, that the wave function of the system collapses, and reality is forced to choose. We will find a cat that is either definitively alive or definitively dead. The question Schrödinger posed was, when does collapse actually happen? This thought experiment pushes the strangeness of superposition from the microscopic realm to the macroscopic world, forcing us to confront the measurement problem. The Heisenberg uncertainty principle, the universe's built-in limits. This probabilistic nature is codified in one of the most famous principles in physics, the Heisenberg uncertainty principle. In 1927, Werner Heisenberg stated that there is a fundamental limit to how precisely we can know certain pairs of a particle's properties at the same time. The most famous pair is position and momentum. The more precisely you determine a particle's position, the less precisely you can possibly know its momentum, and vice versa. This is not a limitation of our instruments. Even with infinitely perfect tools, this uncertainty would remain. It is a fundamental property of the universe itself. A particle simply does not possess a perfectly defined position and momentum simultaneously. Its nature as a wave function forbids it. A wave that is very spread out has a poorly defined position but a well-defined wavelength, which corresponds to momentum. Conversely, to create a wave localized in one place, a well-defined position, you must superimpose many different wavelengths, making its momentum incredibly uncertain. You can have a definite position or a definite momentum, but never both. This principle shows that the starting premise of Newton's clockwork universe, knowing the exact position and momentum of every particle, is impossible. You can never know the initial conditions with perfect accuracy because they do not exist in a perfectly defined state to begin with. The universe has an inherent fuzziness baked into its fabric. Quantum mechanics is not about pure, lawless randomness. It is about probabilistic determinism. The evolution of the wave function itself is deterministic, governed by the Schrödinger equation. But the outcome of any measurement on that wave function is fundamentally probabilistic. The universe plays by a strict set of rules, but they are the rules of probability, not mechanical certainty. We have seen the evidence: the particle that acts like a wave, the cat that is both alive and dead, the fundamental limits of knowledge. Now we must confront the most profound question of all. What does it mean to observe? The observer effect. Does consciousness create reality? We have arrived at the core of the mystery. The dividing line between the quantum world of possibilities and our classical world of definite outcomes appears to be observation. But what is an observation? Does it require a conscious mind? The idea that consciousness collapses the wave function is tantalizing, placing human awareness at the center of creation. However, most physicists today find this idea problematic. The universe existed for billions of years before conscious minds evolved. What qualifies as conscious? A human? An insect? The consciousness causes collapse theory is not supported by scientific research and creates more problems than it solves. A more mainstream explanation is found in the concept of quantum decoherence. The idea here is that a quantum system does not need a conscious observer to collapse its wave function. It just needs to interact with its environment in a way that records information about its state. In the double-slit experiment, to observe which slit the electron went through, we placed a detector there. That detector is a physical system. When the electron interacts with it, a record is created. The information about the electron's path becomes entangled with the state of the detector, and this entanglement quickly spreads to the wider environment. This process, where the system's state becomes hopelessly entangled with its environment, is decoherence. Once the information is out there, the delicate quantum coherence, the ability of the wave function to interfere with itself, is destroyed. The wave-like behavior is lost, and the system behaves like a classical particle. The superposition is effectively gone, not because a mind looked at it, but because the environment measured it. Any interaction with a large, complex environment will do the trick. A camera, or even a single stray air molecule, can act as an observer. This is why we do not see macroscopic objects like cats in a state of superposition. They are constantly interacting with their environment, light, air, thermal radiation, and are measured trillions of times per second, keeping them locked into a single, classical state. And yet, this does not fully solve the mystery. Decoherence explains why we don't see superposition, but it doesn't fully explain the final collapse to a single outcome. It just pushes the superposition out into the environment. The electron, the detector, and the air molecules are now one giant entangled system. This leads us to the final frontier: the different interpretations of what is physically happening. The interpretations. Many worlds, Copenhagen, and beyond. The mathematical rules of quantum mechanics predict experimental outcomes with phenomenal accuracy. But what those rules mean for the nature of reality is still debated. There is no single, accepted answer, but several competing interpretations. 1. The Copenhagen Interpretation. Developed by Niels Bohr and Werner Heisenberg. This is the classic interpretation. It posits a fundamental divide between the quantum world and the macroscopic, classical world. The wave function is a tool for calculating probabilities. When a quantum system is measured, the wave function collapses. Period. According to this view, physics is about what we can measure, and questions about an unobserved reality, like which slit an unobserved electron really went through, are considered meaningless. 2. The Many Worlds Interpretation, MWI*, proposed by Hugh Everett III. This interpretation takes the wave function with absolute seriousness and says it never collapses. Instead, every time a quantum measurement is made, the entire universe splits into multiple branches. In each branch, one of the possible outcomes becomes real. When you open Schrödinger's box, the universe splits. In one universe, you find a live cat; in another, a copy of you finds a dead cat. There is no game of chance. Everything that can happen, does happen, somewhere. The evolution of this multiverse, as a whole, is completely deterministic. 3. Quantum Bayesianism, cubism, *. This more recent interpretation argues that the wave function is not a real, physical object. Instead, it represents the subjective beliefs and knowledge that a particular observer has about the system. Wave function collapse, in this view, is not a physical process. It is simply the observer updating their knowledge after a measurement. Chance, therefore, is a reflection of an individual's incomplete information about the world. There are other interpretations, including pilot wave theory and objective collapse theories. The fact that so many brilliant minds can look at the same results and come to such wildly different conclusions tells us one thing for sure: the universe is far stranger than we ever imagined. Conclusion: a universe of chance. We began our journey in a solid, predictable world, a clockwork universe. But as we peeled back the layers, we found a world built on a foundation of uncertainty and probability. Through the double-slit experiment, we saw fundamental particles live a dual life, their identity shifting based on observation. We encountered superposition, a ghostly state where all possibilities exist at once. We learned of the Heisenberg uncertainty principle, a law that embeds a necessary fuzziness into the fabric of the cosmos, proving the deterministic dream of classical physics was just that, a dream. The universe, at its most fundamental level, is not a story that has already been written. It is a story being written, moment by moment, through an endless series of probabilistic events. The wave function describes the odds, but it does not dictate the outcome. Each interaction, each measurement, is like a cosmic roll of the dice, collapsing a wave of potential into a single point of actuality. Does science suggest the universe is a game of chance? The evidence is strong that chance is not just part of the game, it is the game. Whether this is because reality is fundamentally probabilistic, as some interpretations suggest, or because all outcomes are realized in an ever-expanding multiverse, or because probability is a tool to manage our own ignorance, the result in our experienced reality is the same. The future is not set. We are not just spectators. The act of observation, of interaction, is the very process that seems to coax reality into existence from a fog of maybes. We are woven into the fabric of the cosmos in a way our classical intuition could never have prepared us for. The universe is not a clockwork machine. It is, perhaps, a quantum symphony of possibilities, constantly resolving into the singular reality we call home. The simulation glitch that breaks reality. What if the world around you, the solid ground, the air you breathe, the stars in the sky, isn't quite what it seems? What if there's a glitch in the code of our universe, a fundamental rule that scientists have proven exists, but can't fully explain? This isn't just a thought experiment from a movie. It's a real conclusion, pointed to by one of the most bizarre and mind-bending experiments in the history of science. It's a phenomenon that suggests our world only fully solidifies when we're looking at it. It hints that the universe might behave like a hyper-realistic video game, one that only renders the fine-grained details when a player is actively observing, all to save processing power. In the strange world of quantum physics, when nothing is interacting with them, the building blocks of matter stop being definite things. Instead, they act like ghostly waves of pure potential, existing in multiple places at once. But the moment an interaction happens, the moment a measurement is made, they snap back into the familiar, solid reality we know. This is the story of that glitch. It's the story of the observer effect, and how it might just be the most significant clue that we are living inside a simulated reality. The idea that we live in a simulation has been debated by philosophers for centuries, from Plato's cave to Descartes' evil demon. But in the 21st century, this idea has jumped from philosophy classrooms into serious scientific and technological conversations. Billionaire entrepreneurs, renowned physicists, and computer scientists are all asking the same fascinating question. Are we living in a computer program built by a more advanced civilization? At first, it sounds like science fiction. How could the incredible complexity of our universe be nothing more than lines of code? But what if the code itself has a built-in tell? A weird anomaly in the laws of physics that doesn't quite add up in a purely physical universe, but makes perfect sense if our world is being computed on demand. And that brings us to the core of the mystery. The most famous and unsettling experiment in all of physics, the double-slit experiment. It's here, in the quantum realm, that reality seems to fray at the edges, revealing a behavior so strange it forces us to question the very nature of existence itself. The analogy, reality as a video game. Before we get into the physics, let's start with something more familiar, a video game. Imagine you're playing a huge, open-world game. You're on a mountain, looking out over a vast landscape. You see forests, rivers, and cities in the distance. It all looks real and solid. You'd assume that if you turned around, that world behind you would still be there, rendered in perfect detail. But it's not. To save memory, game developers use a trick called on-demand rendering. The game engine only loads the parts of the world that you, the player, are currently looking at. That city behind you doesn't fully exist as a detailed model until you turn to look at it. The individual leaves on a distant tree aren't calculated until you get closer. The game is conserving its resources, operating on a need-to-show basis. Why waste processing power on something nobody sees? Think about how efficient that is. The game creates a convincing illusion of a solid, persistent world, but it's a clever trick. It's a world that only fully materializes where you direct your attention. Now, hold that thought. What if our universe runs on a similar principle? What if reality only bothers to compute the definite properties of a particle, like its position, when an observer, or any interaction, forces it to. This isn't just a fun analogy. This is shockingly similar to what the foundational experiments of quantum mechanics seem to show. The universe appears to run on an incredibly efficient engine, one that refuses to render a definite reality until it absolutely has to. And the trigger for that rendering? The act of observation or measurement. This idea has been explored by physicists like Dr. Melvin Vopson, who proposes that our universe might be trying to save on data. His speculative work on infodynamics suggests that the information content in the universe tends to simplify and compress over time, which is exactly what a computational system would do to run more efficiently. This is the simulation hypothesis in its most powerful form, not just a philosophical idea, but a potential explanation for the bizarre rules of our cosmos. The laws of physics themselves might just be the side effects of a computational system designed for maximum efficiency. And the biggest clue is the glitch we find when we zoom all the way down. The glitch, unpacking the double-slit experiment. To see the glitch for ourselves, we need to journey into the quantum world with a simple setup: a barrier with two thin slits, a screen behind it, and something to shoot at it. This is the double-slit experiment, first performed with light by Thomas Young in 1801. But its modern version, using single particles, is where things get truly weird. Let's start with something intuitive, like marbles. If we shoot marbles randomly at the barrier, some will bounce off, some will go through the left slit, and some through the right. On the screen behind, we'd expect to see two distinct bands where the marbles hit, lining up with the slits. Simple, predictable, classical mechanics. Now, let's switch to waves. Imagine generating a wave in a tank of water. When it hits the barrier, parts of the wave pass through both slits, creating two new smaller waves on the other side. These two waves interfere with each other. Where their crests meet, they get bigger. Where a crest meets a trough, they cancel out. The result on the screen is a unique signature, an interference pattern, a series of many bright and dark stripes. This pattern is the smoking gun for wave behavior. It proves that whatever went through the slits went through both at once and interfered with itself. So far, so good. Now for the moment reality seems to break. Let's go back to firing particles, but this time, something tiny, a single electron. Electrons are bits of matter. So, if we fire them one by one, we should get the same two-band pattern as the marbles. We start the experiment, firing one electron at a time. The first one hits the screen, making a single dot. Then another, and another. For a while, the dots seem random. But as we fire thousands, then millions, one by one, an impossible pattern begins to emerge. It's not the two bands from the marbles. It's the interference pattern of the waves. Let that sink in. The screen shows the striped pattern of interference, even though we were firing individual particles. This can only happen if each electron, each single particle, somehow went through both slits at the same time, interfered with itself like a wave, and then landed on the screen as a single dot. How can one thing be in two places at once? It's as if you walked toward two open doors, passed through both at the same time, and then showed up as one person on the other side. This is the first part of the glitch. When nothing is looking at which path the electron takes, it doesn't behave like a solid particle. It exists as a superposition, a blurry cloud of all possibilities. Naturally, the physicists who first saw this were baffled. Their logical response was, okay, let's find out which slit each electron actually goes through. So, they placed a detector, a sort of microscopic sensor, right at the slits. Its job is simple. Register when an electron passes through, telling the scientists which path it took. They run the experiment again. The detector works perfectly. One electron goes through the left slit. A second goes through the right. Each electron is now confirmed to be taking a single, definite path, just like a well-behaved marble. Mystery solved, right? Wrong. Because when we look at the screen, the interference pattern is gone. It's replaced by the simple, two-band pattern of the marbles. The moment a detector was turned on, the moment the system was measured, the electrons stopped acting like waves. The very act of measuring which path the particle took forced it to choose a path. It collapsed its wave of potential into a single, definite reality. It's a common misconception that the particle knows it's being watched by a conscious person. Scientific research shows that's not the case. The observer is any physical interaction that extracts which path information, a photon bouncing off it, an electronic detector, anything at all. That interaction is what forces the change. This is the observer effect. The universe seems to have two sets of rules. One for when it's unobserved, a fuzzy, probabilistic world of waves. And another for when it is observed, the solid, definite world of particles we know. It's a reality that doesn't seem to fully commit until you measure it. This has been confirmed with photons, electrons, and even huge molecules. The glitch is real. The question is, what does it mean? We're now deep in the rabbit hole. We have a physical phenomenon that defies common sense and strangely mirrors the efficiency tricks of a video game. If your mind is bending and you enjoy exploring the biggest questions in science, consider subscribing. We explore mysteries like this every week, and by subscribing, you won't miss what's next. Click that subscribe button, and let's keep unraveling the cosmos together. The implications: is this an interpretation of a simulation? The double-slit experiment isn't just a weird party trick. So, what could it be telling us? Why would reality behave this way? One of the most provocative interpretations is the simulation hypothesis. In this way of thinking, the observer effect isn't a mystery, it's a feature. It's a resource management system. Let's go back to our video game analogy. A game engine doesn't waste processing power rendering a world no one is seeing. It keeps things in a state of low detail probability. The enemy across the map doesn't need a defined location until you get close. Its state is just a cloud of possibilities, somewhere in that castle. Only when you enter the castle does the engine compute its exact position. The unobserved electron is like that enemy. It doesn't have a definite path. It exists as a wave function, which is a mathematical description of all its possible paths. The universe, or the processor, doesn't need to waste resources calculating a single history for a particle that isn't being measured. It's computationally cheaper to treat it as a wave of possibilities. But when we turn on our detector, we're basically telling the system, hey, I'm looking now. I need a definite answer. Left or right? This act of measurement is a demand for data. It forces the system to render a result. The wave function collapses, and a single, classical reality is delivered. The interference pattern vanishes because the condition that creates it, going through both slits at once, is no longer allowed. The system was forced to run the high-detail, particle, simulation instead of the low-detail, wave, one. This idea was championed by the brilliant physicist John Archibald Wheeler, who called it the participatory universe. He famously said, "No elementary phenomenon is a phenomenon until it is a registered, observed phenomenon." For Wheeler, we are participants in bringing the universe into being. Every act of measurement crystallizes reality from a sea of potential. If our universe is a simulation, this participation is just us interacting with the program. The laws of quantum mechanics, in this view, are just the rendering engine's rules laid bare. Building the case: more potential glitches. If the observer effect were the only strange thing about our universe, we might just call it a quirk. But if you start looking, other potential glitches or artifacts of a computed reality seem to pop up in the fabric of physics itself. ***1. The processor speed limit, the speed of light. Any computer has a processing speed limit. This creates a hard speed limit on everything inside a simulation. Information can't travel faster than the processor can compute the change. Our universe has a very similar, absolute rule: the speed of light. Nothing can travel faster than it. In a purely physical reality, why should there be an ultimate speed limit? It seems arbitrary. But in a computed reality, it's a necessity. The speed of light could be an analogy for the processor speed of our universe. ****2. The resolution of reality, the Planck length. If you zoom in far enough on a digital image, you see the pixels. The smooth picture becomes a grid. It has a finite resolution. It's a common misconception that the Planck length is a literal pixel of space. More accurately, it's a theoretical, unimaginably small scale where our current understanding of physics and even the concepts of space and time break down. If our reality is a simulation, this could be interpreted as the fundamental resolution of the grid that makes up our spacetime. ***3. Networked particles. Quantum entanglement. One of the most mind-bending quantum phenomena is entanglement. You can link two particles so they become a single system, even if they're separated by galaxies. If you measure a property of one, you instantly know the state of the other, faster than light could travel between them. Einstein called it spooky action at a distance. In a purely physical world, this is deeply weird. How do they communicate instantly? But in a simulation, the answer could be simple. The particles aren't two separate things. They're two outputs linked in the program's code. When you measure particle A, you're not sending a signal to particle B. You're just reading a variable, and the value of particle B's variable is algorithmically tied to it. The distance in the simulated space is irrelevant. ***4. The law of conservation of information. Just as a computer optimizes itself, some physicists suggest our universe does the same. A new line of thinking, spearheaded by researchers like Melvin Vopson, proposes a second law of infodynamics. While the famous second law of thermodynamics says that disorder tends to increase, Vopson's speculative work suggests that information entropy, a measure of information content, tends to decrease over time. This is what you'd expect in a system designed to compress data and run efficiently, as if the universe is constantly defragging its own hard drive. Addressing the skeptics, the counter-arguments. Of course, the simulation hypothesis is a philosophical interpretation, not a proven theory, and it faces significant criticism. First, many physicists argue that the observer effect is just a result of physical interaction. To see an electron, you have to interact with it, and that interaction inevitably changes its state. In this view, there's nothing mystical about it. It's just that quantum measurement is an inherently disruptive act. This is a more conventional interpretation, though it doesn't fully erase the strangeness of why an unobserved particle exists as a wave of pure potential. Second, there's the sheer complexity argument. Critics argue that simulating our universe down to the quantum level would be impossible, requiring a computer larger than the universe itself. Proponents counter this by saying we can't assume the base reality has the same laws of physics, and a simulation would only need to render the observed parts in high detail. Third, there's a strong philosophical objection. We use science from inside our universe to argue for the simulation hypothesis. If we're in a simulation, all of that science could just be part of the program, making the very logic we're using untrustworthy. Finally, and perhaps most compellingly, a 2025 study by physicists including Dr. Mir Faisal and Dr. Lawrence Krauss argues that simulating the universe is mathematically impossible. They contend that the fundamental laws of physics require a form of non-algorithmic understanding that, by definition, cannot be reproduced by a computer program that must follow rules. This presents a powerful mathematical challenge to the entire idea. These are all serious challenges. They remind us that the simulation hypothesis is a fascinating interpretation, but it's not the only one. Other ideas, like the many worlds theory, suggest the universe does take all possible paths. but that each path splits off into its own parallel universe. Conclusion: we started with a simple question. What if our reality is a simulation? We journeyed into the quantum realm and found the double-slit experiment, where matter acts like a ghostly wave of possibilities until the moment it's measured. We saw how this glitch can be interpreted in a way that mirrors the efficiency tricks of a video game. We then looked at other aspects of physics, like the speed of light and entanglement, as further analogies that fit neatly into this framework. The idea that our universe is a participatory reality that we help shape through measurement is one of the most profound shifts in thinking in the history of science. As John Wheeler suggested, we aren't just spectators, we are participants. So, are we living in a simulation? The evidence is far from conclusive, and powerful arguments stand on both sides. But the question itself is transformative. It pushes us to the absolute limits of our knowledge. The next time you look at the world around you, remember the glitch. Remember that at the deepest level, the universe seems to wait for an interaction. It waits for a measurement. And in that act of observation, you might be doing more than just seeing. You might be playing a part in calling the world into being. What do you think? Are these quantum quirks just bizarre features of our universe, or are they signs of an underlying code? Let me know your thoughts in the comments below. Science just proved the universe waits for you. For most of time, the world has felt solid. The ground beneath our feet, the air we breathe, the light from a distant star. They all seem to exist with a quiet certainty, carrying on whether we are paying attention or not. This is a comforting thought, a foundation upon which we build our lives. But in the last century, as we began to look at the world at its most fundamental level, a different picture began to emerge. It suggests that the world is not as fixed as it seems. That beneath the surface of what is, there lies a vast and shimmering field of what could be. This is not philosophy or a daydream. It comes from physics. Some of the most careful and profound experiments ever designed have led to a conclusion that is as quiet as it is transformative. The universe does not simply happen to us. In a very real way, it may be happening with us. Today, we are taking a calm journey into that idea. We will explore the quiet strangeness of quantum mechanics, from the famous double-slit experiment to the thought experiment of Schrödinger's cat, and eventually to a recent discovery that seems to suggest the past is not as settled as we believe. We will look at the evidence that reality does not fully form until something, or someone, is there to interact with it. It is a journey that asks us to reconsider our place in the cosmos, because science is revealing that the universe we experience may be waiting for our attention. Take a moment to think about the space around you. The shape of the room, the objects within it, the world outside your window. You know it is there. Our lives are built on the understanding that the world is an objective place, that it persists when we are not looking. But what if this is the most natural assumption we have ever made, and also the most incomplete? What if, when we turn away, that solid and definite reality softens back into a haze of pure potential? Quantum physics suggests this may not be a what if at all. It may simply be how the world works. The end of common sense. For most of human history, our view of the world was simple and reliable. We called it classical realism. It is the philosophy of the everyday. A stone has a definite weight and a definite location. These properties exist whether we are looking at the stone or not. In this view, the universe is like a grand, intricate clockwork, wound up long ago and ticking along according to fixed and predictable laws. We are observers, watching the mechanism unfold. Our looking at the stone does nothing to change it. It only reveals the reality that was already there. This is the world of Isaac Newton, of solid things and clear paths. For centuries, it served us perfectly. It allowed us to build cities, chart the stars, and understand the rhythms of our world. And then, at the start of the 20th century, we learned to look at the very, very small. And that is when our common sense understanding began to change. The place where it changed was a deceptively simple experiment, one that has been called among the most beautiful in all of science, the double-slit experiment. Imagine a wall with two thin, parallel slits cut into it. On one side, a device fires small particles, like tiny specks of sand. On the other side, a screen records where they land. First, if we fire something like sand, the result is predictable. Some grains go through the left slit, some go through the right. On the screen, two distinct bands form, a pattern that matches the two slits. This is particle behavior. Now, imagine we send waves, like ripples in water, toward the same two slits. Something different happens. As the waves pass through both slits at once, they interfere with each other. Where two crests meet, the wave is amplified. Where a crest meets a trough, they cancel out. The result on the screen is not two bands, but a complex pattern of many bands, a clear signature of interference. This is wave behavior. Here is where the familiar world begins to soften. Physicists decided to fire the smallest things they could find, single electrons. An electron is a fundamental particle, a single unit. It should behave like the sand. We would expect each electron to pass through either the left slit or the right. After firing thousands, one by one, we should see two simple bands. But that is not what happens. As the electrons land, one after another, what slowly builds up on the screen is not two bands, but a full interference pattern. This was deeply unfamiliar. It was as if each electron, all by itself, passed through both slits at the same time, interfered with itself, and then chose a place to land. The only way to get this pattern is if the electron was acting like a wave of pure potential, exploring all possible paths at once. This state, existing in many possibilities at once, is called asterisk superposition. This alone tells an important story about the nature of reality. But the final step is what revealed something quietly fundamental. The physicists, wanting to understand more, decided to watch. They placed a small detector by the slits, a device that would record which path each electron actually took. The moment they did, the moment they observed the electron's path, the interference pattern vanished. What appeared on the screen were two simple bands, just like the sand. The simple act of measurement, of asking the question, "Which path did you take?" seemed to resolve the situation. The electron stopped being a wave of possibilities and became a single particle on a single path. It was as if the universe existed in a gentle superposition of both, until an interaction forced it to become one. This isn't just a quirk of electrons. It has been shown with atoms and even large molecules, with recent experiments in 2026 confirming quantum states in objects of ever-increasing size. The act of observation is not passive. It is a part of the process that turns potential into something actual. The ghost in the machine. The double-slit experiment shows that on the smallest scales, things are not settled until they are measured. But a natural question arises. Does this strangeness stay in the world of single electrons, or can it extend to the world we live in? The world of cats and boxes and people? This question was on the mind of the Austrian physicist Erwin Schrödinger. In 1935, to show how unfamiliar these quantum rules seemed when applied to the everyday world, he created one of the most famous thought experiments in science, Schrödinger's cat. Imagine a cat, placed inside a sealed box. With the cat is a device containing a single radioactive atom. A radioactive atom is a quantum system. Over a certain time, say 1 hour, it has exactly a 50% chance of decaying and a 50% chance of not decaying. It exists in a superposition of both states. Linked to the atom is a detector. If the atom decays, the detector triggers a hammer, which breaks a vial of poison, and the cat dies. If the atom does not decay, the cat remains alive. Now, the box is closed. After 1 hour, according to quantum mechanics, the atom is in a superposition of decayed and not decayed. But because everything in the box is linked, this means the hammer is in a superposition of falling and not falling. The poison is in a superposition of being released and not released. And so, the cat is in a superposition of being both alive and dead at the same time. This is the paradox. Our intuition tells us a cat must be one or the other. But according to the rules of quantum mechanics, the entire system inside the box stays in this undecided, probabilistic state until a measurement is made. The measurement is the act of opening the box to look. In that moment, the quantum state collapses. The universe resolves, and the cat becomes either fully alive or fully dead. Schrödinger meant this as a way to question the theory, but the mathematics behind it was sound. The thought experiment forces us to ask a difficult question. What counts as an observation? And does the definite world we see emerge from a fundamentally indefinite one? This leads to an even more layered paradox, developed in 1961 by Nobel laureate Eugene Wigner. It is called Wigner's friend. This thought experiment adds a second observer, and it suggests that the nature of reality is even more subtle than we imagined. The experiment begins where Schrödinger's ended. A researcher, the friend, is inside a completely sealed laboratory. Inside that lab, the friend performs the cat experiment. She opens the box and sees a definite outcome: a live cat or a dead one. For the friend, a fact has been established. Let's say she sees the cat is alive. But now, consider your perspective. You are Wigner, standing outside the sealed laboratory. You cannot know what the friend saw. From your point of view, the entire lab is one large, interconnected quantum system. Just as the cat was in a superposition for the person outside the box, the entire lab, including the friend, is now in a superposition for you. According to the laws of quantum mechanics, until you open the lab door and ask your friend what happened, the system from your perspective remains unresolved. The friend is in a superposition of having seen a live cat and having seen a dead cat. Here is the quiet revelation of Wigner's friend. There are two observers, and they have two different, but equally valid, descriptions of reality. The friend, inside, says, a definite event has occurred. You, outside, must say, no definite event has occurred. The lab is in a superposition of all outcomes. Who is right? Quantum mechanics suggests that both are. This is no longer just a thought experiment. In recent years, physicists have performed real-world versions of this scenario. A 2018 paper by Kaslov Bruckner provided a theorem suggesting that observer-independent facts may not be possible, and subsequent tests have further solidified the paradox, showing that two observers can experience different, conflicting realities. The conclusion is that there may not be one single, absolute fact of the world, but only facts that are relative to an observer. The universe, it seems, tells a different story depending on who is listening. Erasing the past, we have seen that the world of the very small is a world of possibilities, not fixed things. We have seen that observation seems to be part of the process that makes reality concrete. We have even considered the idea that there may be no single reality, but many realities, each relative to an observer. If that has stretched the imagination, what comes next asks us to be even more open. What if the choice to observe could not only affect the present, but also the past? This is the work of the physicist John Archibald Wheeler. In the 1970s, he proposed a thought experiment that seemed to gently challenge our ideas of cause and effect: the delayed choice experiment. Let us return to the double-slit setup. We know that if we don't watch which path a particle takes, it behaves like a wave. If we do watch, it behaves like a particle. The measurement determines its behavior. But Wheeler asked a simple, profound question. When does the particle decide whether to be a wave or a particle? Wheeler suggested we could wait. We could let the particle pass through the slits, and only after it was already on its way to the screen would we decide whether or not to measure its path. Imagine a version of this on a cosmic scale. Light from a quasar, billions of light years away, travels toward Earth. A massive galaxy sits in its path, acting as a gravitational lens, bending the light and creating two possible paths for it to reach us, just like the two slits. Here on Earth, billions of years after the light passed that galaxy, we have a choice. We can set up our telescope to simply collect all the light together. In this case, we are not checking which path it took, and we should see an interference pattern, wave behavior. Or, at the very last moment, we could use two separate telescopes to see which path the light came from. This would be a measurement of its particle behavior. Wheeler's proposal was that our choice today determines what the light did billions of years ago. If we choose to look for interference, the light will have behaved as a wave, traveling both paths at once. If we choose to see which path it took, it will have behaved as a particle, taking only one. The past, in Wheeler's words, is an unperformed experiment. It does not have a settled history until it is observed in the present. This idea has been tested and verified in laboratories. And the experiments have led to an even stranger version, known as the delayed choice quantum eraser. In this experiment, a special crystal splits a photon into an entangled, twin, pair. One photon, the signal, goes toward a detector screen. Its twin, the idler, goes to a different set of detectors. The setup is arranged so that by measuring the idler photon, we can learn which slit its signal twin went through. First, we let the signal photon hit its screen. Its position is recorded. A pattern of scattered dots appears with no interference. This is because the which path information is available from its twin, even if we haven't looked at it yet. The universe knows the information exists, so the signal photon acts like a particle. But here is the delay and the eraser. Long after the signal photon has already landed, we choose what to do with its idler twin. We can measure it in a way that tells us which path its twin took. Or, using a series of mirrors, we can erase that information, scrambling it so it's impossible to know. When we later look at the recorded data from the signal photons, something remarkable is found. If we sort the signal photons based on their twins whose path information we did not erase, they show no pattern. They landed as particles. But if we look only at the signal photons whose twins had their information erased, an interference pattern appears out of the data. An action we took in the present, erasing information, seemed to alter the nature of an event that had already happened. The choice to measure or erase determines what the reality was. The past, it appears, is not just unknown, it may be genuinely undecided until a future interaction brings it into focus. A 2017 cosmic bell test used starlight to decide measurement settings, confirming quantum predictions over vast distances and reinforcing this strange, relational view of reality. You can think about this in a simpler way. The GPS on a phone receives signals from many satellites. In a way, your location is a superposition of possibilities defined by all those signals. The act of you asking, "Where am I?" is the interaction that collapses those possibilities into a single point on a map. Your location wasn't fixed until you chose to observe it. What is reality, then? We have journeyed to a place where our familiar ideas feel distant. We have seen that observation is an act of participation, that facts can be relative, and that the past may not be a fixed story. This leaves us with a quiet, monumental question. If reality is not the solid, objective thing we thought it was, then what is it? Here, physics touches philosophy, and there are several ways to understand the story. The first, and for a long time the standard view, is the Copenhagen Interpretation. In its simple form, it is very pragmatic. It suggests that physics is not about what reality is, but about what we can observe. A property-like position doesn't truly exist before a measurement. An electron exists as a wave function, a mathematical description of all its possibilities. The act of measurement causes this wave function to collapse, randomly selecting one possibility to become real for us. The universe, in this view, is fundamentally probabilistic. There is no deeper layer. The observation doesn't just reveal a state, it helps create it. The difficulty with this view has always been its vagueness about what counts as a measurement. This ambiguity led to a second, more expansive idea, the many worlds interpretation. First proposed by Hugh Everett III, it takes the mathematics and follows it to a logical, if staggering, conclusion. It asks, what if there is no collapse? What if, when a measurement is made, all possibilities happen? In this view, every quantum measurement causes the universe to branch. When the friend opens Schrödinger's box, the universe divides. In one universe, she sees a dead cat. In a parallel universe, she sees a live one. Both outcomes are real. Your choice simply determines which version of the universe you experience. This neatly resolves the Wigner's friend paradox. The friend sees a definite outcome because she is on one branch. You, outside, describe a superposition because you have not yet branched with her. Both descriptions are correct in their own context. It is an elegant idea, but it requires us to imagine a near infinite number of parallel worlds being created in every moment. But there is a third way of looking at this, one that is gaining quiet acceptance. Relational quantum mechanics, RQM**. This view suggests that our mistake has been in our language, our concept of things having properties. What if reality is not made of things, but of interactions? Proposed by physicists like Carlo Rovelli, RQM states that a system's properties are not its own, but exist only in relation to another system. An electron does not have a position. It only has a position relative to the detector that interacts with it. Reality is a network of relationships. Properties only manifest through interaction. The universe is not a noun, it is a verb. It is a constant becoming. In this framework, your interaction is your entry into a dance of potential. You and the system you observe co-create a moment of actuality, a definite event, relative to you. This also helps us understand our world. The reason large objects feel solid is a process called decoherence. A cat is constantly interacting with trillions of air molecules and photons. Each tiny interaction is a measurement, collapsing its quantum possibilities almost instantly. This constant interaction pins the cat down into a single, stable state relative to its environment. It is why we do not see living and dead cats. The cat is constantly being observed by the world around it. Yet, this does not fully resolve the paradox for a perfectly isolated system, and it leaves us with the central, transformative idea. Reality emerges from interactions. And our consciousness, our act of asking questions, is a profound form of interaction. If this kind of calm exploration into the nature of reality helps you see the world in a new way, consider liking the video and subscribing to the channel. We go on these journeys each week, and we would be glad to have you with us. So, we return to our opening question. Does the universe wait for you? After this journey, the answer seems to be more subtle and beautiful than a simple yes or no. The universe does not wait like a finished painting, waiting for a light to be turned on. It is something more alive, more participatory. The evidence from the double slit, from Schrödinger's paradox, and from the delayed choice experiments all points toward the same quiet conclusion. The world is not a collection of finished objects. It is an ocean of potential. It is a field humming with every possibility, all existing at once. Our classical world, the world of definite things and a linear past, is not the fundamental reality. It is an emergent reality, drawn out of that potential through interaction. And observation, the act of a conscious mind engaging with the universe, is a powerful form of that interaction. We are not just spectators watching a play that was written long ago. We are part of the process that brings the story into being. Every time we look, every time we measure, we are taking part in the transformation of the ghostly, maybe, of the quantum world into the definite, of our experience. Your reality is constantly being formed, moment by moment, through your relationship with it. So, the next time you think about the room around you, remember that the question of its existence is more meaningful than it seems. The world you experience is real, but it is a reality that may be actualized in relation to you. What science has shown is not that the universe depends on us for its existence, but that we are an inseparable part of the process that makes it real. What do you think? Are we living in one branch of an infinite tree? Or is reality a continuous dance of becoming? We would be interested to hear your thoughts in the comments below. What reality did you just help bring into focus? The universe that exists for no one. Imagine a performance for an empty auditorium. A cosmos of impossible beauty, where galaxies spiral and stars die in spectacular silence, with no mind to ever see it, no one to feel the awe. If a universe plays out its entire story but is never witnessed, did any of it truly matter? This isn't just a thought experiment. This is, perhaps, the most profound question we can ask about reality itself. We are so used to our role as the audience, the ones who give names to constellations and meaning to the changing seasons, that a universe without us feels fundamentally incomplete. Almost broken. But for the vast, overwhelming majority of its history, this is exactly what the universe was. A grand, intricate, and impossibly complex show with no one watching. An opera sung into an indifferent void. To feel the weight of this, we have to journey through that silent cosmos. We have to see a universe that wasn't meant for any eyes. A story that, for billions of years, had no one to tell it to. This is the story of everything, seen by no one. Part 1. The narrative of an unseen cosmos. Before our ideas of time and space meant anything, there was something for which we have no words. Then, in a flash of unimaginable energy, the universe was born. Not to a waiting audience, not to applause, but into a deep and profound silence. The first light blazed through the cosmos, a wave of pure creation expanding into an endless dark. But there were no eyes to see this light, no minds to be stunned by its brilliance. It simply was, a fact without a witness. For 380,000 years, that light was trapped in a hot, dense fog of particles. When the universe finally cooled enough for it to break free, it painted the entire cosmos in a faint, lingering afterglow. We call it the cosmic microwave background. Today, we see it as a blueprint left in an empty workshop, a relic of the universe's first moments. But for eons, it was just a pattern. A complex message in a bottle, floating on an ocean with no shores, and no sailors to find it. Slowly, almost patiently, gravity began its work. In the quiet emptiness, the smallest wisps of hydrogen and helium, the universe's only raw materials, began to pull on each other. Over millions of years, these wisps became clouds. The clouds became clumps, and the clumps collapsed, igniting a new kind of fire. The first stars. Picture a star erupting in the absolute dark. A thermonuclear furnace, enormously massive, blazing with a furious, blue-white light. A beacon in an ocean of indifference. But this incredible spectacle happens in a vacuum not just of space, but of appreciation. There are no names for the constellations these first stars form. No myths are written about their light. They are born, they burn through their fuel in a geological blink, and then they die. And their death is even more spectacular than their birth. These first, giant stars end their lives in cataclysmic explosions, the first supernovae. In a final, defiant roar, a single dying star can briefly outshine an entire galaxy. And in this fiery crucible, new elements are forged. The simple hydrogen and helium of the early universe are crushed together to create carbon, oxygen, iron. The very building blocks of everything we would one day become. These elements, the ashes of dead stars, are scattered like seeds into the void. This cosmic shrapnel will one day become planets, asteroids, and eventually, living things. But for now, it's just debris. The fallout from a war no one saw. The universe is following its own rules, playing out a drama on an unimaginable scale, but the auditorium is still empty. As the eons drift by, these enriched clouds are drawn together again. Not into single, lonely stars, but into vast, sprawling cities of them. The first galaxies, islands of light in the ever-expanding darkness. At their centers, supermassive black holes form, the quiet, unseen rulers of these stellar cities. And these galaxies are not still. They move, they dance. Over billions of years, they are drawn towards one another in a slow, silent ballet. Two spiral galaxies, each a masterpiece, pull and stretch each other's arms into long, glowing tendrils. They pass through one another like ghosts, their structures merging in a chaotic, beautiful scramble until they settle into a new, larger galaxy. A monument to a union that no one ever celebrated. Inside these galaxies, the cycle of birth and death continues, unseen. Stars are born in glowing nebulae, stellar nurseries sculpted into pillars of gas and dust light-years high. Imagine canyons deeper than 1,000 solar systems, and mountains of hydrogen glowing with reflected light. These are some of the most beautiful structures in the entire universe. And for billions of years, they exist in absolute anonymity. And on the quiet outskirts of one such galaxy, an average, yellow star is born. Around it, leftover dust clumps together. One clump becomes a small, rocky planet, a molten ball of fire, a violent and hellish place. Slowly, it cools. Water arrives, forming the first silent seas. An atmosphere takes shape. It is a world of sterile rock and quiet oceans. Nothing moves but the wind and the waves. This is Earth, for the first billion years of its life. A perfect stage, waiting for actors that might never arrive. The universe has spent nearly 10 billion years setting this stage. It has forged heavy elements in stars, built galaxies from dust, and formed a planet with liquid water. All of this, a chain of events so improbable it borders on the miraculous, has unfolded in complete and total solitude. There is no meaning here. Not yet. There is only physics, chemistry, and the cold ticking of a clock with no one to hear it. This is the great cosmic dread. The deep, unsettling feeling that all this beauty, all this complexity, all this magnificent, pointless grandeur, might ultimately be for nothing. This is the universe that exists for no one. A silent masterpiece. And it is in this profound silence that the story is about to change forever. Part 2. The pivot, the observer changes everything. For billions of years, the universe played out like a predictable machine. But what if that was only half the story? This is where our journey takes a sharp turn, from the cosmic scale down to the bizarre, counterintuitive world of quantum mechanics. A world where the simple act of looking at something changes what you see. The door to this new reality is the double-slit experiment. It's the clearest proof we have that reality is far stranger than it appears. Imagine firing tiny particles, like electrons, one by one at a wall with two thin slits in it. If you close one slit, the electrons that get through make a single band on a screen behind it. They act like tiny pellets. Simple. But when you open both slits, something impossible happens. The electrons, still fired one at a time, don't make two simple bands. They create a complex pattern of many bands. An interference pattern. This is the signature of a wave interfering with itself. It's as if each single electron passes through both slits at the same time as a blurry wave of possibilities, before landing on the screen as a single particle. This is where it gets truly strange. Physicists, baffled, decided to place a detector by the slits to see which one each electron actually went through. The moment they looked, the interference pattern vanished. As soon as they were observed, the electrons stopped behaving like waves and went back to acting like solid particles, creating two simple bands. It was as if reality itself was camera shy. A landmark 1998 experiment confirmed it. The more watching that occurred, the less wave-like reality behaved. This is the observer effect, and it forces us to ask, does observation not just reveal reality, but actually create it? This question has split physics into three radically different stories about what it means to exist. Story 1. The Copenhagen Interpretation. Reality waits for a look. This was the first and, for a long time, the dominant idea. Proposed by pioneers like Niels Bohr and Werner Heisenberg, it's stark and revolutionary. It says an electron simply doesn't have a definite position before you measure it. It's just a cloud of mathematical probability. Observation here isn't necessarily a conscious mind. It's any interaction with a large-scale measuring device. That interaction is what forces the fuzzy cloud of possibilities to collapse into a single, concrete reality. In this view, the unseen cosmos wasn't just unobserved. It was, in a very real sense, undefined. A universe of pure potential, waiting for the first interaction to make it real. Story 2. Many worlds. The universe never chooses. Other physicists found the collapse unsatisfying. In the 1950s, Hugh Everett proposed a wild alternative. The wave function never collapses. Instead, every time a quantum measurement could have different outcomes, the entire universe splits. When an electron can go through slit A or slit B, it does both, in separate, parallel universes. In one, it goes through A, in another, it goes through B. You just happen to find yourself on one of those branches. The problem? Without an observer to experience a branch, the many worlds universe becomes a sterile, infinitely complex mathematical object. A library containing every book imaginable, but with no one to read them. The theory designed to get rid of the observer ends up making an observer the only thing that gives any single branch meaning. Story 3. Observer-free physics. Everything is watching everything else. A third path suggests we're asking the wrong question. Perhaps everything is observing everything else all the time. In this view, any physical interaction is a measurement. An atom on a train doesn't need a physicist to measure it. Its properties are already being defined by its interactions with everything around it. Consciousness plays no special role. The universe is a constant, frenetic dance of particles measuring each other. But this leads to its own puzzle. If reality is just this web of interactions, then the solid chair you're sitting on is just a statistical average, an appearance. But an appearance has to be an appearance to someone. For whom does it appear? This leads to the deepest layer of the puzzle, the Wigner's friend experiment. Imagine a scientist, the friend, in a sealed lab who measures an electron. For her, reality has collapsed. She sees a definite result. But for you outside, the entire lab, friend, electron, and all, is now one giant quantum system in a superposition of seeing one result and seeing another. So, who is right? Recent experiments suggest that both of you are. Reality itself might be relative to the observer. The universe we imagined, lonely, silent, but solid, is starting to look like a fairy tale. The very fabric of existence seems to be a ghostly, undefined fog of pure potential, waiting for a witness. The arrival of the first observer, then, isn't just an interesting plot point. It might be the moment the story begins to be written at all. This doesn't have to be a person. It could be the first self-replicating molecule, its shape determined by quantum interactions. But mind, a conscious observer, that's something else entirely. It doesn't just record what happens. It asks why. It finds patterns. It tells stories. It looks back at the 13.8 billion year journey and gives it a name. It gives it meaning. Part 3. The empowering conclusion. We've journeyed through a silent cosmos and plunged into the quantum realm, where reality itself seems to wait for a witness. We are left stranded between two unsettling ideas. A universe that means nothing because no one is watching, and a universe whose very reality depends on being watched. And here, in this strange landscape, we find the most powerful perspective of all. Let's return to our lonely planet. In its warm, shallow oceans, something new is happening. A soup of chemicals, forged in the hearts of long-dead stars, is being stirred by lightning and sunlight. After countless random combinations, a molecule forms that can make copies of itself. This is the spark, the first quiet flicker of life. It's not conscious. It's a chemical machine, but it's also the first true observer on our planet. Its replication depends on specific quantum interactions. With every bond it forms, it turns the fuzzy potential of the quantum world into the hard actuality of its own existence. It is the universe, for the first time in this quiet corner, beginning to write its own history in the language of DNA. For billions of years, this is the only observation. Life diversifies, fills the oceans, and begins to remake the entire planet, pumping oxygen into the atmosphere. The show is still playing in an empty hall, but now a tape recorder has been switched on. Then, after a 4-billion-year journey of trial, error, extinction, and survival, a new kind of observer emerges. One with a network of neurons so complex it can become aware of itself. Consciousness. This is the true pivot of the entire cosmic story. With a conscious mind, the universe is no longer just being recorded. It is being witnessed, understood, appreciated. The light from a star 1,000 light-years away is no longer just photons. It is now starlight. The intricate patterns of a snowflake are no longer just a crystal lattice. They are now beautiful. The death of a star is no longer an anonymous act of physics. It is a asterisk supernova, a source of awe. This is the ultimate reframe. Our awareness doesn't retroactively create the Big Bang, but it imbues the entire 13.8 billion-year story that led to this moment with a significance it never had on its own. The meaning of the past is fulfilled by the present. Think of it like a lost symphony. A brilliant score sits in a dusty archive for centuries. Its value is latent, waiting. When a musician finally discovers it and performs it, the genius of the composer is finally realized. The music doesn't begin to exist in that moment, but its purpose does. We are those musicians. We are the universe's way of knowing itself. The atoms in our bodies were forged in stars. After billions of years of silent evolution, a small part of the universe has woken up. And this changes everything. The loneliness of the cosmos is not a sign of its meaninglessness. It is the scale of the achievement. It means that meaning is not something we are given, it is something we create. If we are the ones who get to witness this spectacle, that doesn't make us insignificant. It makes us astronomically precious. It hands us a profound responsibility. We are the custodians of meaning. When we study geology, we are the cosmos remembering its own youth. When we study astronomy, we are the cosmos mapping its own body. When we create art, we are the cosmos reflecting on its own nature. The universe that existed for no one was a tragedy of solitude. But the universe that, against all odds, gave rise to someone, is a story of triumph. So, does a universe that is never observed have meaning? Perhaps the question is flawed. Our existence doesn't erase the silent eons that came before. It redeems them. It is the flowering of a seed that was planted at the very beginning of time. Our lives are fleeting. Our species will one day vanish. But for one brief, shining moment, a part of the universe was awake. A part of it knew wonder. A part of it looked up at the stars and felt a connection to the vast, silent story that produced it. And that, perhaps, is enough. That for a cosmic instant, the universe was not for no one. It was for us. And our act of witnessing, of understanding, and of cherishing this improbable existence, gives meaning to the whole damn thing. The questions we've explored are some of the biggest we can ask, and the conversation is far from over. So, what does this mean to you? Do you think reality needs a witness to be real? Or is meaning something we create entirely for ourselves? Share your perspective in the comments. The best conversations happen when we explore these mysteries together. And if you enjoy grappling with life's biggest questions, consider subscribing for more journeys into the cosmos and the mind. Conclusion. We began with a lonely image, a universe of breathtaking beauty playing out in absolute solitude. We saw how this cosmic loneliness can feel like a story without a point. But we've also discovered a powerful counter-narrative. The strange rules of the quantum world hint that our presence might be woven into the fabric of reality itself. And even if it's not, the arrival of consciousness is still the moment the universe gains a witness, the moment its story can finally be told. The final takeaway isn't one of dread, but of empowerment. If we are the universe made conscious, then our lives are not meaningless accidents. They are the culmination of a 13.8 billion-year epic. Our curiosity, our art, our science. These are the tools the universe uses to understand itself. We are not separate from the cosmos looking in. We are the cosmos, experiencing itself. And in a universe that for so long existed for no one, that makes our brief, fragile, and beautiful existence the most meaningful thing of all. Science discovered a glitch in the universe. Take a moment to consider the room around you. The floor beneath your feet, the screen you are watching, the quiet presence of the air. They feel solid, persistent, real. Our minds are built on the certainty that the world exists, with or without us. It is a deep and necessary intuition, one that has guided every step of our existence. But what if that feeling, as certain as it seems, is not the complete story? What if science, in its quiet exploration of the universe, has found that at the very smallest scales, reality behaves in an unfamiliar way? This is a journey into that discovery. It is not a story of monsters or myths, but of a rule in the fabric of the cosmos so counterintuitive it feels like an error. The discovery is this: the universe seems to respond differently when it is measured. And the story of why this is so difficult to accept is not just about physics. It is about where we come from, and why our ancient instincts for survival are in conflict with the fundamental nature of things. Welcome. If this kind of calm exploration into the world helps you unwind, consider liking the video and subscribing. And wherever you are right now, feel free to share where you're watching or listening from. The unsettling discovery. To understand this quiet glitch, we have to begin with the world we expect. We call it classical physics, or more simply, realism. It is the world of predictable paths and solid objects. When a ball is thrown, we believe it has a definite position and speed at every moment. We may not know these properties, but we trust that they exist. The moon has a location, a tree is either standing or has fallen. These properties feel objective, separate from any observer. For centuries, this model of the world worked perfectly. It helped us build bridges and chart the course of planets. And then, at the start of the 20th century, we opened a door into a new place, the quantum world. And the predictable clockwork began to look unfamiliar. The first hint of this strangeness came from a simple experiment, now perhaps the most famous in all of physics, the double-slit experiment. The design is straightforward. There is a barrier with two small, parallel slits. On one side, a source shoots tiny particles, like electrons. On the other, a screen records where they arrive. If you were to do this with something familiar, like microscopic grains of sand, the result is predictable. Close one slit, and a single band forms on the screen. Open the other, and a second band forms. Open both, and you see two bands, one behind each slit. This is the world as we expect it. But when this experiment was performed with electrons, something else happened. With both slits open, the screen did not show two bands. It showed a pattern of many stripes, a pattern of interference. This is the signature of a wave. It is what happens when ripples in a pond meet, reinforcing in some places and canceling out in others. The only way for an interference pattern to form is if the electron was not behaving like a particle, but like a wave, passing through both slits at once and interfering with itself. A single electron seemed to be in two places at the same time. It existed not as a definite point, but as a wave of possibility, a superposition of its potential paths. This is where the glitch truly reveals itself. The physicists, understandably puzzled, wanted to know which slit the electron really went through. So they placed a detector at the slits, a small device to record the path of each electron. The moment they did this, the moment they observed the path, the interference pattern vanished. In its place were two simple bands, just like the grains of sand. The act of measuring which path seemed to correspond with the electron abandoning its wave-like state and behaving like a particle with a single path. It was as if the electron's behavior was linked to whether it was being watched. The universe, at this fundamental level, behaved differently when measured. This is a difficult thing to accept. The outcome of the experiment depended on whether a measurement of the path was made. When unobserved, the electron is a wave of potential. When observed, it becomes a definite particle in a single location. This is often called the observer effect, and it has been confirmed by countless experiments for nearly 100 years. It is not a metaphor. It is a fundamental rule. Properties we assume are solid, like position, do not seem to exist in a definite state until an interaction, a measurement, takes place. Reality, it seems, is not a fixed stage, but a participatory event. An unwritten past. If the double-slit experiment felt like a subtle crack in the foundations of reality, the next step in this journey makes the story even stranger. The physicist John Archibald Wheeler, a man who worked with both Einstein and Bohr, wanted to push this idea to its logical conclusion. He designed a thought experiment, one so unusual that it took decades for technology to perform it. It is called the delayed choice experiment. The setup is our double-slit experiment, but imagined on a cosmic scale. A photon of light leaves a distant quasar, billions of light years away. On its journey to Earth, its path is bent by the gravity of a galaxy, which acts like a lens. This creates two possible routes for the photon to reach our telescope, one around the left of the galaxy, one around the right. This is our double-slit setup, expanded to an astronomical size. Here on Earth, we have a choice. We can set up our telescope in one of two ways. In the first mode, we can look for interference, which will only happen if the photon traveled as a wave along both paths at once. In the second mode, we can instantly switch our equipment to determine which path the photon took, left or right. This will only work if the photon traveled as a particle. Here is Wheeler's quiet twist. We wait to make our choice. We decide whether to measure for a wave or a particle after the photon has already passed the galaxy. The light has been traveling for billions of years. It passed those galactic slits long before human life, or even Earth, existed. Now, in the last moment of its journey, we choose how to observe it. Our intuition tells us that the photon must have been either a particle or a wave billions of years ago. Our choice now could not possibly reach back in time and change what has already happened. And yet, when physicists finally performed this experiment, the results were consistent with this strange idea. If they chose to measure which path the photon took, the results showed it had behaved like a particle, taking a single route. If, at the last second, they switched to look for interference, the results showed it had behaved like a wave, having taken both routes at once. The choice made in the present determined what we could say about the photon's past. This does not mean we are changing the past, but something more subtle and just as profound. It suggests that there was no single, fixed story of the photon's journey to begin with. The history of the photon, whether it was a wave or a particle, whether it took one path or two, did not exist in a definite form until the observation was made. It remained an open question, a cloud of possibilities. This is a deeply unfamiliar conclusion. Our classical idea of a single, unfolding history does not seem to apply at the quantum level. The universe does not appear to fill in the details until an act of measurement forces it to. It is as if reality is a story that is not just unread, but unwritten until a reader looks at the page. The universe has no secret plan. At this point, a very reasonable question arises. Perhaps this is simply a matter of incomplete knowledge. Perhaps the electron or photon does have a definite path, but its properties are hidden from us. This idea is known as hidden variables. It was the preferred explanation of Albert Einstein. He felt that quantum mechanics must be an incomplete theory. There must be, he argued, some secret information carried within a particle that predetermines the outcome of any measurement. In this view, our observation simply reveals a property that was always there. It is like finding one glove from a pair. If you find the left-handed glove, you know instantly that the other is right-handed. The information was encoded from the start. This concept, called local realism, rests on two intuitive assumptions. Realism is the idea that objects have definite properties even when not observed. Locality is the idea that an object can only be influenced by its immediate surroundings. For decades, the debate between Einstein's hidden variables and the standard quantum view seemed to be a philosophical one. Then, in the 1960s, a physicist named John Stuart Bell devised a mathematical theorem that could put the idea to a test. His theorem, now known as Bell's inequality, proved that if the universe operated on local hidden variables, the results of certain experiments would have to obey a specific statistical limit. However, if quantum mechanics was correct, and reality was truly probabilistic and non-local, that statistical limit would be violated. It was a direct challenge. Perform the experiment and see which description of the world is more accurate. This brings us to the work that was recognized with the 2022 Nobel Prize in Physics. Three physicists, John Clauser, Alain Aspect, and Anton Zeilinger, turned Bell's theorem into a series of careful, precise experiments. The experiments involved creating pairs of entangled particles, where two particles are linked in such a way that their fates are intertwined, no matter how far apart they are. In 1972, Clauser was the first to build a working experiment, and his results showed a clear violation of Bell's inequality. They matched the predictions of quantum mechanics, not local realism. Alain Aspect followed with more refined experiments, closing potential loopholes. Anton Zeilinger later took these experiments to new levels of precision, each one confirming the same quiet truth. The conclusion from 50 years of these Nobel-winning experiments is inescapable. There appear to be no secret instructions or hidden variables predetermining a particle's state. The properties of a particle are not just unknown before measurement, they seem to be genuinely undetermined. They do not exist until an act of observation coaxes them into being. As one of the laureates, Anton Zeilinger, stated, "We had to give up the idea of realism to a far greater extent than most physicists believe today. This is no longer just a matter of interpretation. It is an experimental fact, a discomfort of the mind. The unease we feel when facing these quantum truths is not a failure of intellect. It is something deeper. The feeling of rejection, of a quiet, internal voice saying, 'That cannot be right,' is a predictable result of our own evolution. Our minds were not built for quantum reality, because they were not built in quantum reality. They were shaped on the savannah, in a world governed by the logic of survival. For millions of years, the most important task for any organism was to make accurate predictions about its environment. Is a predator hiding in the grass? Will a branch hold my weight? In this world, objective reality was not a philosophical idea, it was what kept you alive. Our brains evolved as prediction machines, operating on the assumption that the world is persistent and independent of us. A tiger in the bushes must exist whether you are looking at it or not. To believe the tiger only appears the moment you see it would be a fatal error. The brain that survived was the one that treated the unseen world as just as real as the seen world. This is our intuitive realism, a kind of default operating system hardwired by natural selection. It demands that objects have definite properties. Uncertainty, in that environment, was a danger. Then, science reveals a world where, at the fundamental level, this intuition does not hold. It tells us that an electron can be in a superposition of multiple places at once. It presents a universe that is fundamentally probabilistic and responsive to observation. This creates a profound cognitive dissonance, a conflict between the rules of the world we see and the rules of the world underneath. Even Albert Einstein felt this, once asking a colleague, "Do you really believe the moon is not there if you are not looking at it?" This was the expression of a mind, one of the most brilliant in history, encountering a truth that violates its most basic, evolutionarily programmed assumptions. His intuition, like ours, was shaped for a world of rocks and tigers, not wave functions and probabilities. Quantum mechanics does not say the moon vanishes when you are not looking. Large objects are constantly interacting with their environment, with photons, dust, and gravity, which keeps them in a definite state. This process is called decoherence. But this does not change the underlying rule. The reason the moon is there is because countless other things are, in a sense, looking at it. The underlying glitch remains. Reality at its base is a dance of potentiality, not a statement of fact. So when we feel that sense of deep unease, we are feeling the echo of our ancestors. We are hearing a warning coded into our minds for millennia. Trust that what you do not see is just as real as what you do. It is a powerful and necessary illusion for survival. But an illusion it appears to be. An unwritten story. The implications of an observer-dependent reality go beyond physics. They touch upon our ideas of existence, self, and our place in the world. If reality is not a fixed backdrop, but a participatory process, what does that make us? This leads to one of the most quiet and unsettling thought experiments ever proposed: Wigner's friend. Conceived by Nobel laureate Eugene Wigner, it extends the measurement problem to its most difficult conclusion. Imagine a physicist, the friend, inside a perfectly sealed laboratory. She performs a quantum measurement, for example, on the spin of a particle. The moment she observes the particle, its wave function collapses, and she sees a definite result, such as spin up. For the friend, a fact has been created. Now, consider Wigner, the super observer, standing outside the sealed lab. From his perspective, the entire lab, the friend, the particle, the measuring device, is one large, unobserved quantum system. According to the rules of quantum mechanics, Wigner must describe the lab and his friend as being in a giant superposition. A state of friend who has seen spin up and friend who has seen spin down at the same time. Here is the paradox. The friend, inside, has experienced a definite reality. But for Wigner, outside, she remains in a blurry superposition until he opens the door and observes her. So, when did reality become definite? When the friend looked at the particle, or when Wigner looked at the friend? This thought experiment challenges the idea of a single, objective reality. It suggests that what we consider a fact might be relative to the observer. Recent, more complex versions of this experiment have led to even more challenging conclusions, suggesting that we cannot simultaneously hold three intuitive assumptions: that there are objective facts, that we have free choice, and that influences are local. The Nobel-winning experiments already cast doubt on locality, leaving a difficult choice between the other two. This is not to say that only one's own mind exists, but it does redefine the relationship between the observer and the observed. It softens the line between our awareness and the external world. We are not watching a film that has already been made. We are, in some quiet and mysterious way, co-creators of the reality that unfolds with every interaction. The glitch is not an error in the system. It may be the system itself. The world does not just exist, it becomes. And we are part of that becoming. Conclusion: we began with a simple question. Is the room still there when you close your eyes? We have journeyed from the double-slit experiment to the edge of space and time, and have seen Nobel Prize-winning evidence that the universe does not seem to have a pre-written plan. We have found that the discomfort we feel is not a failure of understanding, but an evolutionary echo, a survival instinct from our deep past. We live a divided existence. We walk through a classical world, our brains shaped for solid things and predictable events. Yet, the technology in our lives, the transistors that power our screens, the lasers in our computers, all function because we have learned to use this quantum strangeness. We are navigating our world with an ancient, intuitive map, while building our future with tools from a reality that map cannot describe. Perhaps the glitch is not a bug at all. Perhaps it is the most important feature. It suggests that we are not separate from the world we observe. It suggests that reality is not a static noun, but an active verb. It is a continuous process, a quiet dance between what is possible and what is actual, a story being written with every observation. We may never fully shake the feeling that the ground should be solid. But science has shown us a different, more subtle truth. We are not just standing on the ground. We are helping to create it. You are forcing reality to exist and science can prove it. You probably think your eyes are just windows, passively showing you a world that's already there. You wake up, see your room, see the sky, and figure you're just watching a movie that started billions of years ago. That reality is a fixed, solid thing that exists just fine without you. But what if science's most profound and mind-bending discovery is that you're not just watching the movie? What if, in a strange way, you're helping to direct it? What if the simple act of looking, of observing, plays a crucial part in compelling the universe to take a stand? This isn't some New Age mysticism. It's an idea that springs from the very bedrock of quantum mechanics, the most rigorously tested theory in all of science. And the experiment that launched this idea, which we're about to explore, might just change the way you see everything. It suggests that you aren't just a passive witness to the universe, but that your very act of observation is what helps collapse a wave of infinite possibilities into the single, concrete world you experience every day. The clockwork cage, the world of classical physics. To really get how radical this is, we need to rewind a bit. For centuries, our universe was understood through what we now call classical physics. This was Isaac Newton's world, a place of beautiful, predictable, clockwork precision. Picture the universe as a giant game of pool. If you knew the exact position, speed, and angle of every ball at one moment, you could, in theory, predict the entire future of the game. Every collision, every path, all of it would be predetermined. This was the dream of a deterministic universe. In this view, reality is objective. The moon is there whether you look at it or not. A tree falling in a forest absolutely makes a sound, because sound is just pressure waves, a physical event that doesn't need eardrums to exist. In this clockwork cosmos, you and I are just cogs in a vast machine. Our thoughts and feelings? Just the exhaust fumes of brain chemistry. We're simply watching a story written at the dawn of time. This led to the idea of Laplace's demon, a thought experiment about a god-like intellect that could know the location and momentum of every atom in the universe. For this being, the past and future would be an open book. No chance, no mystery, no free will. Everything was set in stone. For a long time, this model worked perfectly. It sent rockets to the moon and powered the Industrial Revolution. It gave us a sense of mastery. But as the 19th century wound down, scientists saw cracks in this perfect clockwork facade. Strange things started bubbling up from the microscopic world of atoms, things that refused to play by Newton's rules. The cracks in reality, problems with the old view. Take the old model of the atom. A mini solar system, with electrons orbiting a nucleus like planets around the sun. There was just one tiny, catastrophic problem. According to classical physics, an orbiting electron should constantly radiate energy, lose speed, and spiral into the nucleus in less than a second. If that were true, every atom in the universe would have collapsed almost instantly. The simple fact that you and everything around you exist was a direct contradiction of the best physics of the time. That was the first big clue that the rules for the very small were totally different from the rules for the world we see. Another head-scratcher was the ultraviolet catastrophe. When physicists used classical laws to predict the energy radiated by a hot object, their own equations predicted it should emit an infinite amount of energy. That's obviously absurd. Something was deeply wrong. A new physics was needed. And in the early 20th century, it arrived. It was called quantum mechanics, and it didn't just rewrite the rules, it lit the rulebook on fire. It introduced ideas that felt like magic. It told us energy comes in discrete packets, or quanta. It said particles like electrons could also act like waves, spreading out like ripples on a pond. And most disturbingly, it revealed a fundamental uncertainty at the very heart of reality. The clockwork universe was dead. In its place was something far stranger, and way more participatory. The experiment that broke physics, the double-slit. At the heart of all this quantum weirdness is one of the most elegant and baffling experiments ever devised, the double-slit experiment. It's the best way to see the central mystery of quantum mechanics and understand the provocative claim in our title. Let's walk through it. First, imagine a wall with two thin, parallel slits. We'll fire tiny marbles at it, one by one. On the other side, a backstop records where they land. What do you expect to see? Easy. Two stripes of hits, right behind each slit. This is classic, common-sense particle behavior. Okay, now let's switch from particles to waves. Picture waves in a water tank moving toward the slits. As they pass through, they spread out and interfere with each other. Crests meeting crests make bigger waves. Crests meeting troughs cancel out. On the backstop, you don't get two bands. You get an interference pattern, a whole series of alternating bands. That's the signature of a wave. So, the rule is simple. Particles make two bands, waves make an interference pattern. Now for the quantum leap. We'll use a device that fires one single electron at a time. An electron is a particle, a tiny piece of matter. So, it should act like a marble, right? It has to go through either the left slit or the right slit, eventually forming two bands. So we run the experiment. We fire the electrons one by one. The first one hits here. The second one hits there. At first, the impacts look random. But as we let thousands pile up, a jaw-dropping pattern emerges. It's not the two bands we expected. It's an interference pattern. Let that sink in. The electrons, which we fired one by one like tiny particles, created a pattern as if they were waves. It's as if each electron passed through both slits at the same time and interfered with itself. This is the first shock of quantum mechanics. Particles exist in a state of superposition. Before they're measured, they aren't in one specific place. They're a wave of probability, a smear of potential. But it gets even weirder. The physicists who saw this were baffled. They thought, okay, we just need to know which slit it's asterisk really going through. Let's find out. So they placed a detector, a tiny metaphorical camera, right at the slits to record which path each electron took. Now we can watch. We fire an electron. The detector clicks. Right slit. The electron hits the backstop. We fire another. Click. Left slit. And so on for thousands of electrons. And what pattern do we see on the backstop now? The interference pattern is gone. Vanished. In its place are the two simple bands we'd expect from marbles. This is the central mystery that shatters our common-sense view of the world. By setting up a detector, we physically interacted with the electron to find out its location. And that very act of interaction, of measurement, seemed to force the electron to make a choice. The moment it was measured, its wave of possibility collapsed into a single, concrete particle reality. It's as if the electron dropped its weird wave act and behaved like a normal particle because it was being watched. This is called wave function collapse, and it's the strange and debated transition from the fuzzy, probabilistic quantum world to the definite world we actually experience. The trigger? Measurement. Interaction. It seems the universe doesn't commit to a story until it's observed. Before observation, the electron was a ghostly wave of possibilities. After, it was a definite particle in a definite place. A specific reality emerged from a sea of possibilities. The ghost in the machine. What counts as observation? This experiment drops a huge, unsettling question in our laps. What, exactly, is an observer? What counts as a measurement? In the experiment, the observer was just a simple detector. It seems any physical interaction that extracts information, no matter how small, is enough to collapse the wave function. You can't see an object without light bouncing off it and hitting your eye, which changes the object. You can't check your tire pressure without letting a little air out, changing the pressure you're trying to measure. In the quantum world, that disturbance isn't a side effect, it's the whole show. The interaction creates the property being measured. So, does that mean consciousness isn't required? Can a rock be an observer? This is where the debate explodes, leaving physics and entering philosophy. Many physicists, following the Copenhagen Interpretation, would say consciousness is totally irrelevant. A Geiger counter, a photographic plate, even a stray air molecule bumping into the electron could count as a measurement that destroys the superposition. In this view, collapse happens constantly as quantum systems interact with their environment through a process called decoherence. But that just pushes the question back a step. What makes a Geiger counter a classical device while the electron is quantum? A Geiger counter is just a big pile of atoms, all following quantum laws themselves. So why doesn't the whole lab, the physicist, and the entire universe just exist in one giant superposition of all possible outcomes? Where do you draw the line between possibility and certainty? This is called the measurement problem. This puzzle led some of the most brilliant minds in physics to entertain a more radical idea. Physicists like John von Neumann and Nobel laureate Eugene Wigner pointed out that there's one observer that is undeniably different from any other: a conscious mind. You can imagine a detector in a superposition, but you can never describe your own experience that way. You either saw the electron go left, or you saw it go right. You're never aware of both at once. Wigner formalized this with his Wigner's friend thought experiment. Imagine a physicist, the friend, in a sealed lab. She's going to measure an electron's spin, which can be up or down. Outside the lab is Wigner. From his perspective, the entire lab, friend, machine, and electron, is one big quantum system. The friend makes the measurement. She sees a definite outcome. Let's say, spin up. For her, reality has collapsed. But for Wigner outside, it's different. Since he hasn't interacted with the lab, he must describe the whole thing, his friend included, as being in a superposition. In his equations, his friend is in a bizarre state of having seen spin up and spin down at the same time. So, who's right? Wigner's startling conclusion was that the collapse only becomes final when the result enters a conscious mind. He proposed that consciousness plays a unique role in the universe. This is a very controversial idea, but it was his attempt to solve the measurement problem. We are definitely heading down the rabbit hole now, from a simple experiment to the nature of consciousness itself. If this is expanding your mind, take a second to subscribe and hit that bell icon. We explore these big questions where science and philosophy meet every week. Your support helps us keep asking them. Now, let's see just how far this goes. Proof of no objective facts? For decades, Wigner's friend was just a philosophical puzzle. But recently, quantum technology has gotten so good that physicists have run real-world versions of this scenario. In a groundbreaking 2019 experiment, a team created an extended Wigner's friend setup. The details are mind-bending, but the conclusion was stunning. The results suggested that the facts of the world could be different for different observers. The friend inside the lab could measure and record one fact: spin is up, while Wigner outside could prove that, from his perspective, the friend and her measurement were still in a fuzzy state of superposition. Basically, it showed that two observers can have conflicting, yet equally valid, accounts of what happened. This doesn't mean nothing is real, but it does powerfully challenge our comfortable, classical notion of a single, objective reality that everyone shares. It points toward a reality that is relational and observer-dependent. This is the core of an interpretation called relational quantum mechanics, RQM, championed by physicist Carlo Rovelli. RQM says there is no absolute, God's eye view of the universe. An object's properties only exist relative to an observer. For the cat in Schrödinger's box, it's either alive or dead. For you outside, it's in a superposition of both until you open it. RQM says both descriptions are correct, relative to their observer. This completely flips our intuition on its head. We think of red or fast as properties of an object. But RQM says properties aren't inherent, they are the result of an interaction. Reality, in this view, isn't a collection of things, but a vast network of relationships. The great debate, competing visions of reality. Now, it is absolutely essential to say that the idea that consciousness collapses the wave function is a fringe interpretation. Wigner himself had doubts later in life, and today very few physicists subscribe to it. But the puzzle it tries to solve, the measurement problem, is so thorny that it has led to other, equally mind-bending theories. The most standard view is the Copenhagen Interpretation. It's more pragmatic. It basically says the job of physics is to predict the results of experiments, not to tell you about some hidden reality. The wave function is a mathematical tool for calculating probabilities. When we measure something, the math says to collapse the function, and that's that. Don't ask what's really happening. For many, this feels like dodging the question. To avoid the whole messy collapse business, another wild idea was proposed by Hugh Everett III in 1957. The Many Worlds Interpretation, MWI. MWI says the wave function never collapses. Instead, every time a quantum measurement could have multiple outcomes, the entire universe splits. When the friend measures the electron, the universe splits in two. In one universe, she sees spin up. In a parallel universe, a copy of her sees spin down. According to Many Worlds, every possibility is real somewhere. There's a universe where you ate a different breakfast, took that other job, and won the lottery. It's a clean theory, but it comes at the cost of an infinite, ever-branching multiverse. So we have a menu of strange options. Copenhagen says don't ask what's real. Many Worlds says everything is real. And relational views suggest reality is co-created through interaction. There is no consensus. The experiments rule out our simple, old-fashioned, objective reality, but they haven't yet been able to distinguish between these competing quantum ideas. You, the director, the participatory universe. This brings us to one of the most visionary thinkers in physics, John Archibald Wheeler. He coined the terms black hole and wormhole, and became obsessed with the role of the observer. Wheeler took the lessons of these experiments and synthesized them into a breathtaking concept he called the participatory universe. He argued that we should replace the word observer with participator. Why? Because an observer just watches. A participator has a hand in what happens. Wheeler famously summarized this with the phrase, it from bit. He proposed that the fundamental stuff of the universe isn't matter or energy, but information. And how does information come into being? Through the yes, no questions we ask the universe in our experiments. Every time you make a measurement, even just by looking, you are registering a bit of information. Is the electron here? Yes. Is it spin up? No. Wheeler argued that this process of getting answers is what creates reality. He wrote, "No elementary phenomenon is a phenomenon until it is a registered phenomenon." This is a wild statement. It means the unobserved universe is just an undefined, quantum foam, of possibilities. Our acts of participation reach into that foam and crystallize what's actual. He even designed a delayed choice thought experiment, since confirmed in labs, that seems to show we can decide if a photon behaved as a particle or a wave after it has already passed the slits. To Wheeler, this wasn't a paradox. It was a sign that the universe is a story that only acquires meaning and form through the participation of observers. He saw a grand cosmic loop. The universe gives rise to conscious participators, and those participators, through their observations, give reality to the universe. This isn't to say you can wish for $1 million and make it appear. The laws of physics still provide the menu of what's possible. But in Wheeler's poetic vision, it is our participation that selects from that menu and makes one of those possibilities real for us. Conclusion. The world you choose to see. We started with a simple idea. Reality is something we just watch. We journeyed through the clockwork universe, only to see it shattered by quantum rules. We stood before the double-slit experiment and saw the act of looking change the outcome, forcing a wave of potential into a concrete fact. We peeked into Wigner's lab and faced the idea that reality itself might be relative. What all this science points to is a profound shift. The world may not be a static photograph we're all looking at. It might be more like an infinite, shimmering cloud of every possible photograph at once, a sea of pure potential. And your awareness, your interaction with the world, is what brings one of those images into sharp focus. You aren't just a spectator. You are the point at which the universe looks back at itself. The science doesn't have all the answers. The debate between Copenhagen, many worlds, and participatory models is still raging. But all of them steer us away from a simple, mechanical reality and toward a universe that is far stranger and more deeply tied to the act of observation than we ever imagined. And that has real meaning for how you live. If the reality you experience is crystallized by observation and interaction, then where you place your focus is a profoundly creative act. Your attention isn't just a spotlight. It's more like a chisel, helping to carve your experienced reality from the infinite block of potential. In a very real way, you are helping to bring your world into being, moment by moment, with every glance, every measurement, every conscious act. So the final question isn't just, what is reality? The question is, if your focus helps shape your world, what will you choose to look at?